If you're not using straight C to build your web apps, you're not gonna make it in this economy. Okay, not really, but C is still very important for every programmer to understand so that we can understand how code runs on our machine. And that's not just my opinion, that's also TJ's opinion, who happens to be teaching this course. There's a reason that our backend developer track, which starts students in Python to teach CS fundamentals and ends in Golang to teach backend web servers, actually has one course in the middle in C. This course, storing values within variables in your programs, it's not magic. That data has to actually live somewhere, in RAM on your machine. And by using C to understand memory management from the ground up, we can have a better understanding of how our code actually interacts with the hardware. So even if you work day to day with a programming language like Go or Python or, God forbid, JavaScript, if you understand how your computer works, when you run into hairy memory issues, which frankly, most issues on web servers, in my experience, are memory related, you'll understand fundamentally what's happening on the machine so you can debug it, even if you're not using straight C. In this video, TJ DeVries, renowned maintainer of both NeoVim and Telescope.nvim, is going to walk you through this course, his course, on memory management in C. There are 101 hands-on lessons in this course that will take you from learning the very basics of the C programming language all the way up to building your own garbage collector. In this course, we'll cover C basics, structs, pointers, enums, unions, the stack and the heap, advanced pointers, the stack data structure, building our own objects, and we'll finish off by building 2 garbage collection algorithms from scratch. First, a ref count garbage collector, or reference counting garbage collector, and second, a mark and sweep garbage collector. Now, with all the content that's packed into this thing, it's actually no surprise that TJ took an entire 9 months to build this course. And that's not even counting all of the time that myself and the rest of the boot dev team put into editing, revising, and producing this course. And just like all of the courses that we publish on boot dev, this is not meant to be passively consumed. So head over to boot.dev, make an account, don't worry, it's free, and you can follow along with every single one of the lessons. I actually recommend that you do every single one of the lessons before you watch TJ do it. Use him as sort of a guide and check your answers against him, but you should really be doing it on your own first. Now, all the content in this video, and actually all of the content on boot dev, is free to read and watch. You do not need a paid membership in order to take this course. But if you do want the full interactive experience, then a paid membership will get you things like our AI chatbot boots, solution viewing, progress tracking, and even a shiny certificate when you complete the course. And a membership won't just get you this course, but actually every course on boot dev, including our entire backend development career path. So if you do want a membership, use code TEAJ for 25% off. That doesn't just support us being able to make more of these videos, it also helps directly support TJ. Let's learn how memory management works in C.
Hey everybody, and welcome to my course about C and memory management on boot.dev. Today we're going to do a walkthrough through the entire course, all, I believe, 101 lessons, and I hope you really enjoy it and learn a few things along the way. The idea of this course is that, hey, you might not be writing C professionally. You might never do that. It might be that no matter how you write C, it's never how a professional would do it. But there are a lot of things that you can learn, both about garbage collected languages, manually memory managed languages, as well as other languages like maybe Rust, through doing this course and by building a better understanding of what is going on when the computer has to manage memory for your programs. So without any further ado, let's just go ahead and get started. There's a few things that we're targeting to do throughout this course, and this will give you a little preview of what's coming up. The first one is what's going on in memory. How are things stored on the computer? How do things get turned into ones and zeros, right? Then we're going to sort of be talking about how can we make things more efficient as you begin to think about memory in a more clear and real way. We're going to get some practice in a proper low-level language like C, and at the very end of the course, we'll be building 2 different kinds of garbage collectors to give you a firmer grasp of what languages like Go or JavaScript are doing. In terms of what we're looking for prerequisites, you should just know how to do a little bit of coding. There's no C requirements at all, but it's really hey, I'm not going to explain exactly what functions are. We're going to assume that you know what functions are, like returning something from a function or a loop. If you know those things, you're going to be fine. And throughout the project, what we're kind of going for is building this idea of snakelang, completely unrelated to any other language that you know. And we're not really going to build the entire language, right? It's more along the lines of we're going to be building different aspects of what you would build if you were building a programming language. So we'll build a simple object system and then work on garbage collection for those objects. We're not like writing a garbage collector for C. That would be crazy, although it's been done. And so for our very first lesson, we just have to do something very simple, which is we'll look over here and it'll say, hey, someone confused our beautiful snakelang with Python. Oh, how could they do that? So we just need to update this to say starting the snakelang interpreter. So we can just write snakelang, not snakelang. That would be embarrassing. Click submit and boom. There we go. And you should see a little bit of achievements and we're off to the next lesson.
Now you're probably wondering, okay, so we're going to learn about managing memory. How are we going to do that? Well, we're going to use C as a vehicle for that understanding. This course isn't primarily motivated as the best way to learn C. Instead, we're going to use C as a way to express ourselves to the computer about what we want it to do with memory. Now, I don't want you to be worried. We're going to start all the way from how do I get my very first C program to run and take you step by step from there all the way up to using structs, enums, unions, even a little bit of macros, all along the way so that you can have a strong understanding of the language before we start implementing more difficult aspects like our own little object system, a ref counting garbage collector, and a mark and sweep garbage collector. There are a few things that we won't be covering in the course, like we won't be covering different build tools, different versions of C, or random foot guns that you encounter once your C project gets past 1 million lines. That's not the main focus of the course. Instead, we're trying to give you the tools and the language to understand what's going on when you're running code on the computer or when your garbage collector runs when you're using some language like Python, Go, or JavaScript. With all that being said, let's go make our first C program, which is just going to do the classic printing something out to the console.
In Python, like we mentioned in the video, we have an interpreted language. Now, it does some other stuff. It's got some special, doodads going on these days and everything. But basically what you can think about is, Python starts at the top, goes down to the bottom of the file. If you put a print statement, it'll print it. It'll just do that, right? That's not what happens in C. Here we have the simplest C program, which is just something that says int. This tells us the return type. Main, this is like the entry point, the main place that you're going to run the code. And then it'll have some body of a function, right? If you're not used to this, the curly braces here denote the start and end, okay? And we've got these little semicolons. They're very important in this language. They're not optional like in JavaScript, and they have to be here, unlike white space based Python. We need the semicolons, okay? So what we're going to do here is we're going to do the simplest sort of first program here, which is just we're going to write now everything ourselves. One of the things you'll notice as we work through the course is I do try and make you actually have to sort of physically type out all of the stuff so that I just feel like you actually learn it a lot better when you do it that way. So we'll say include standardIO.h, right? And then we're going to do something like int main, just like we mentioned here. And then we need to do printf hello world. And then we're going to do this little guy here, which you might be thinking, what's going on there? And then we can do return 0. But actually, the program is program in C. So we can do that. We can say program in C. And let's just explain a few of these pieces. The first part, this include, we're going to talk about what's going on here. But for now, you can sort of think of this as like an import. Okay, we're going to cover that more later. Printf means print formatted. Okay. And this is a string, and this guy here tells it to do a new line. So it makes it go there, goes to a new line like that. This is a really good example, I think. Nice. That's cool. I'm sure this doesn't look stupid at all. Too bad for me, right? And so once we do this, then we return 0 at the end. So we should be able to get this when we're submitting here as well. And we've got that. So that's our very simple program, right? Maybe some includes at the top, a main function, the body of the function, and then Main is kind of special. You don't actually have to write return 0, but I like to get in the habit of remembering to do that. So let's go to the next lesson. So now we're to the point where we're thinking, okay, let's compare this to some language that we have some experience with on boot.dev, right? And so the first thing here is if you're thinking, what's going to happen when we run this Python code here? Well, we start, it's got a line for printing, it calls a function that doesn't exist, and then print finished. And our options are a stack trace, do non-defined function prints, right? It just says, hey, this isn't defined. Starting prints, and then a stack trace. Starting prints, then finish prints. So fortunately, Python is not so crazy as to just let you call functions that don't exist. So that one's definitely off the table. So basically, it's between these top two options. And here's where you have to remember, right? Python is interpreted. So it's going to start at the top line. And it says, okay, print starting. And it's like, I can execute that line. So that happens. And then it gets down to the next line and says, func that doesn't exist. Now I'm going to have an error. So that's going to be starting prints, then a stack trace due to undefined functions. Nailed it. If your only experience with a compiler is using the glorified linter, commonly known as TypeScript, then you're in for quite a treat here. We're going to be talking about some of the distinctions between interpreted languages and compiled languages. On the one hand, we have interpreted languages like Python or JavaScript. Examples of some compiled languages would be things like Go or Rust. C fits into that compiled language standard. The primary distinction for interpreted versus compiled, although this line occasionally gets a little bit blurry, is that interpreted languages have some sort of interpreter that runs and executes the code line by line. Now, that's not really true anymore. Computers are much more complicated than that, and we figured that running things line by line actually makes stuff really slow and bad. So lots of languages have things like just-in-time compilers or JITs. Let's leave those aside. We're going to talk more broadly in the sense that if you run Python and you're walking down the file and you run into a function that doesn't exist, that's when you're going to get the error. It won't happen when you first run Python my file, it will happen later. Compare this to compiled languages, which generally speaking have some sort of compiler that actually checks some sort of type system when they're done. That type system can range from incredibly elegant and beautiful, like OCaml, to simplistic and painful to work with, like Go. Shout out to Lane for this diss. Either way, the compiler is going to do some checks ahead of time, turn your source code into some sort of executable, and then allow you to run that executable directly. In general, compiled languages are a bit more performant than interpreted languages. Now, there's a huge range here. Some compiled languages are still very slow, and some interpreted languages have gotten very fast. It's not always that every piece of code written in a compiled language is going to beat an interpreted one. However, generally speaking, you should be comfortable saying a compiled language probably faster than interpreted. As I mentioned previously, one of the other things that's quite nice is that a compiled language will let you know that there's an error at compile time rather than waiting until running into that problem during execution. Now, there's different classes of bugs that can be caught by compilers. You'll find that the C compiler often does not help you, but you'll find that the C compiler generally does help you with certain things like functions that don't exist, fields that don't exist, or variables that don't exist. It is able to catch those, and that is quite helpful during the development cycle. One of the other benefits of compiled languages is that, generally speaking, you can run or execute the binary without bringing the entire language to another computer. So, for example, when you download an executable from the internet, just any old website, and you just run it because it says .exe, what could go wrong? That's a compiled language building that so that it can be executed on another computer. As opposed to if you download a Python script, you're going to need Python on the host program to run that script. Some cons for compiled languages is that depending on the size of the project and the compiler itself, the compilation step, the part that takes your source code and turns it into something that can be executed, can take a long time. I know people for whom this XKCD meme of
doing whatever they want while they're waiting for things to compile would be an acceptable behavior at work, because they literally can't do anything until the compilation step is done, and it could take on the order of minutes or hours. The other con that defenders of interpreted languages will often make is that when you have a compiled language, you always have to fix all of the things the compiler is warning about before you're able to execute anything. This can be kind of annoying if you're trying to iteratively test some small thing and you know you're only going to run over this part of the code. You might not care that other parts of your product are now erroring. You just want to test this little block. And it is true that a compiled language will then just prevent that from happening. So there is something to be said about a rapid iteration speed that sometimes an interpreted language might make easier to do than something that's more statically typed and compiled.
So given that C does something before it actually starts executing, right? We know that it can't run this code at all when this doesn't exist. We can see this by clicking run here, and it says, hey, that function doesn't exist. True. Thank you, C. Good point. I will keep that in mind. So what do we need to do? It says, hey, we can just remove this. So we can delete the line. Now we can click submit. And now we'll all be happy because it's going to work. C has two kinds of comments. The first one is it can do 2 slashes at the beginning, and then everything up to the end of the line is a comment. But sometimes you want to write, more than one line's worth of comments. And in that case, you can do this /* and then a closing */, and everything inside of that is a comment. So it looks like Prime wrote this code here because we are missing this comment here. Once we close the comment, we can submit this, and then everything will be happy in this file. Now we're going to start covering some of the basic types inside of C. The sort of simplest one, the one that we've already encountered, is int for an integer. So 0, 1, 2, 3, 4, 5, etc. Right? We have floats, which are a floating point number. So like 1.23. Also 1.0 is also a floating point number, right? So any number that you would traditionally think of as like a decimal. We have char or car, or I don't know, people call it lots of different things. I usually do char, even though I know that would mean it would be like character. I don't care. It looks like char when I read it this way, and so that's what I'm going to continue doing. You can yell at me in the YouTube comments if you don't like it. I don't care. And then the other important one for us to get started with is char star. And the star, we're going to cover it. Don't worry. I promise. We're going to cover everything you need to know for that. But here, what we need to know here is this is basically just like an array or like a list of characters. Okay. So it could be like, we just have a nice chunk of memory, and then all in a row, we have a bunch of characters in a row. What does that sound like? Oh, a string, right? And so this is basically like, kind of like a string. C doesn't have strings. Yeah, I know. I know. But that's okay. We'll be able to still do things like make it pretend that we have strings, because that's what C does, okay? In this case, what are we trying to do? We're going to try and make sure that we note that, hey, when we define something in C, we can't just say variable equals something else, like you might do in Python, right? Instead, we have to describe what the type is of that thing, and then below here, we're going to print them out. So in this case, we need to make sure that that's a whole number integer, so we can just say int. In this case, we have a single character, so we're going to say char. And then in this case, we have a floating point number, a decimal place, right? So we're going to call it float. Once we do that, all of these prints should now work, and that will be very nice. You'll notice these have different formatters, sort of format specifiers, if you will. We'll cover that more later too. Don't worry. As I alluded to in the previous lesson, most languages have a proper string type, but C does not. There are some, I would say, good, probably like pretty good historical reasons why this was the case. And, in some ways, some of it played out nicely, I guess. But in general, it's like a little bit painful compared to what you're used to. So whenever you see a double quoted sort of list of characters like this is a char star, okay? And so what we can do now is, in your brain, until we cover more info, just replace char star with string. That's like really bad idea normally, but in your head for now, that's good enough, okay? So we just need to say, hey, we need to declare what type this thing is. So that's char star. And so we will never hear again, hey, TJ, when is the memory course in C going to be done? Because it's actually done and we're doing it right now. It's a little meta, but that's great. One thing that you might be confused about is that in C, this like A is different than this. So usually like that's not the case. Maybe in other languages you've done, single and double quotes are interchangeable. This is a char and this is a char star with only one element. Okay, so this won't work if we do like char a equals this. When we try and run this, it's going to say, yo, you can't actually do that. That's not allowed. This is actually a char star, and this one is a char like a single quote like this. Those are two different things, okay? So you can't just interchange those however you'd like, okay? Those need to actually look like this to work. So we'll go ahead and delete those because we don't need them. We'll submit. But that's an important difference that you might not catch up on if you're used to those being interchangeable. Now let's dive a little deeper into printing variables. So the thing we need to do here is that unlike in Python and some newer languages, we can't just do like a little squirrely brace here and just expect the language to figure out how to put a string inside of this other string. That doesn't actually work, okay? So in C, we use format specifiers, and the common ones, and really, realistically, pretty much the only ones we're going to need besides maybe a 1 for printing pointers in this course are %d for digit, right, which is integer, right, format it like digits, C for character, F for floating point, and S for string, which is, once again, really char star. Okay, but like we're calling it string for now. So when you see something like this, print F, right, hello, %s like this, right? So this is going to assume and will check, is this variable a string, right? Is that a string? And then is this one an integer? And there's some implicit conversions that can happen in C, mostly so that there's just more foot guns for you to shoot yourself with. But that's fine because most of the time it works out okay, right? So in this case, it's going to say hello, and then it's going to put name into the first one and age into the second one. And so name needs to be a string and age needs to be in it. The other one that we'll normally see is we need to include a /n at the end of the line to print it as a new line because printf does not automatically do that for us, right? I mean, there's times where you might want to print multiple times to the same line. And so that's what you do here. C doesn't have like optional arguments and stuff like you could do in Python where you can tell it like don't put the new line or do and everything like that. So that's what printf does. And so now what we need to do is we need to print off each of the different values here so that we can complete this lesson. So it's going to look like printf, right? And then what we need to say is default max threads. And then we'll do %, and then we're looking, okay, so it says default max threads. That's here, that's an int, right? And so we need to go %d like this because that's the digit for an integer, right? And then a new line. So then we do snakelang default max threads like this. And we'll keep on going down the line here and do custom perms. And then this one is a char, so we'll do %c. And that's snakelang default perms. And then another print here. And so we'll write constant pi value. Remember, this is a float, so that's %f. Snakelang default pi. Not very precise, but it'll probably do for most cases, right? And then snakelang title. And then that's going to be %s because it's a string. Snakelang title. Let's see if I typed everything correctly first. I don't want to mess up my perfect streak. So we're going to click run first. Oh, it looks good. It looks good. Nice. We got it. Okay. So you can see how each of these different specifiers we can change. We can say something like print this like a float, like it'll still work. It'll convert between. Now it's going to print it like a float. So that's just something to be aware of as you're going through here. Sometimes you can get away with using the wrong thing because of implicit conversions, but in general, you don't want to do that. I would explicitly convert the two, which we'll talk about later. Okay. So one thing up until now you might have noticed is that we're always making sure we only define like one variable as one type the whole time. Now you might be wondering, do we need to do that, or is that just a nice idea? When you compare in like Python, you can just set x equal to any value, and then you can do that again. And you could make it a number, and then a string, and then a Boolean, and then none, and then a string again. I mean, don't do this, but it's possible, right? In C, we cannot do this. We cannot start something as like a char star and then later just change it to a number or some other type. That's not allowed. In the same sort of scope, a value always has to be the same type until we're all the way done with that scope. So in what is okay, in blank, it's okay to change the type of an existing variable. That would be Python. It always lets you do crazy stuff like that. Boom, we got it. However, just because a variable's type cannot change doesn't mean that a variable's value cannot change, right? So variables are by default mutable, right? So we can have x is 5 here, and we can change this to x equals 5. Totally fine, totally fine. So in this code below, though, what you'll notice is we cannot re-specify the type. This is like a declaration, right? This is a declaration. And then this is like we're redeclaring it in the same scope. That's not good. That's not what we want to do. We want to make sure that when we declare, we only declare it once. So when we run this, it's going to say, hey, you've already defined it. The way that we can fix that is we just remove sort of the type definition here. Now, instead of being declaring a new variable, this is just updating the value of an existing variable. So when we submit this, now we should get everything working. But C actually does give us some methods to make it so that we can't just mutate stuff, which is nice. In Python, I guess you would just like make all the letters uppercase and be like, hopefully no one changes this. So in C, we can say const here, which basically modifies the rest of the declaration on the line, right? So we have const like this, and then the rest of it saying this, like this int x is going to be constant, okay? So that means when we do now try and set x equals 10 later in that file, it won't let us. The compiler will check that and say, no, no, no. So of our options here, const int, I see const int, meaning of life 42. Boom, we got it. You might have noticed so far that all of our functions in C do have to sort of specify their return value, but we also need to specify the arguments to functions. So what we see here, right, is float is the return type. That's right here. Add, that's the name right here. Then we have int x and int y. So it takes two parameters, right? The first one is an int and the second one is also an int. And then inside of our body here, right, what we've got going on here is we've got this little like... You know, I get like that kind of looks goofy as you're like, is it putting a function in here and then calling this or something? No, what that actually is this says, hey, when you see something like left parenthesis, a type name, and then right parenthesis, this is saying cast, like the expression to the right of this, to my type. Okay, so this is saying I've got this float thing here. So cast the result of these things, these two things, into a float. So in this case, like an integer plus an integer, that's going to be an integer, right? All the time. But saying, hey, return it like it's a float, and C will convert that integer to a float, right? So in this case, it's kind of silly, right? Because it's like, why would you just add two integers and get a float? Well, it's so that you can see how this is happening and easily converting, right? So when we get the result, now when we do %f, which is what we talked about before for format specifiers, we get that 15.0000000, right? Because we've just added two integers, which is a float with zeros. So it's nice. It's good. If we removed this, you should get an error. I mean, I guess like maybe some compilers won't warn you and stuff, or depending on your flags, but like most normal setups will tell you that that's not allowed, even if ints can be sort of implicitly converted. So what we've got here for our assignment, write a max snake-length memory function in the space provided. It should accept two arguments, max threads and memory per thread, and it should return an integer representing the total memory available to the snake-length interpreter. So just like we've been doing before, it says, hey, we need to return an integer. So that's int. And then we have max snake-length memory. And then we have our first argument, max threads, and we have our second argument, memory per thread. And we're going to return max threads times memory per thread. And we're going to put this where I said to put this in the lesson instead of down at the bottom, because that seems like a good plan. And that should be good. That should be good. So we'll give it a submit. We'll see if we keep our streak. Come on. Oh, nice. You do got to worry like, ooh, what if I mistype something? But no, we got 100% accuracy. Let's keep it moving. There is one type that is special and kind of different from all of the other types, and that's the void type. There's basically two ways that we're going to be used void. The first one is it's an explicit way to say that a function takes no argument. In general, you probably should write it this way. We may not always do it in the course because that sometimes will distract you from the main point. But like if you were writing it, there's a good practice to be including void to say, hey, this thing takes no arguments. That's like its type is no arguments. And when a function doesn't return anything, we can also use void to say, hey, like there's no return at the end of this function. It's not that it returns a value of none or a value of nil. No, it has nothing. There's nothing there. There's nothing at all. It's void. So that's one of the key distinctions maybe from something like in Python, right? Which is that like none is a value. It's just the none value. But in C, there is no like void value. So which is not valid. Void x equals none. That sure looks not valid to me. Void SSH terminal shop. Ooh, great place to get coffee. Void print hello, void. And it, yeah. So the only one here is we cannot set anything to a value that is void. That's not allowed. It's not a reasonable thing to do. So we'll click that. We'll keep moving. Now we're going to start getting into some goodies. So we're going to move from what we've been doing up till now, which is mostly just like printing results, and that's how we check if things are working, to do more of a unit test style. This will let you have a little bit more flexibility in how you write the code and also make it a little more obvious what exactly the expectations are. We're using the mu unit framework. It's really nice, pretty small framework overall. And we have just a little bit of, I would say, a little pizzazz sprinkled on top to sort of I don't want to say hide, but sort of just obscure some of the complications of getting the test framework set up and other things like this. And so we'll look through here as we're going. But basically the main idea as we're working through the rest of this is you'll see something like munit case. This is like a mu unit, right? Here, and this is going to say, okay, we're going to, this is on a run. So if you don't know, boot dev has run versus submit. If you're just watching this, it doesn't really make a difference, but this is going to say we want to run this on run. This is our test get average function. And then here's the body, and we have some asserts of what we're trying to do inside of it. And so basically you'll see some of these cases come up. And then at the end, we list all the cases, we run them, and then we assert whether it works or not. So in this case, when we run this here, it's going to say, hey, we don't actually have a function get average. Okay, that's what we have to do in this lesson, okay? So that's basically what's going on with munit. And what's nice is we've started to explore some of the other things that are going to go on in C. The first one you'll see is we have this main.c. That's kind of like our test file. It's going to be what executes, and it includes all of the test code. We can't change this. There's no way to change it as we go through the other exercises. And usually we have some .h file. We also cannot change that. The H stands for header, and this is what gets included both into the main C here with include exercise H, and we'll also include it when we get inside of here with include exercise.h like this. And what we need to do is our job is to implement this code. One of the things that's pretty cool about C is H file, header files, they kind of declare like a specification of the functions that you're going to implement or types or whatever, right? So here's what we need to do. We need to go ahead and implement a function that returns a float, and it takes 3 integers together and then returns the result. So what we're going to do here is we're going to say something like, and in this case, it's not strictly required that we include exercise H, but it's good practice to do. Get average, and we said int x, int y, int z, right? And now we need to return something here. So the easiest way for us to do this here, and we can check our tips, it says, okay, operator adds numbers 1, 2, 3. Yeah. So this part's pretty easy, right? Because you would think maybe off the top of your head you'd go x plus y plus z, and then just go divided by 3. But if the numbers here are integers, we're going to do integer division. That's not good. So what we need to do is we need to tell ourselves, hey, we actually want to make this a float so that we can do this. And we can just be a little more explicit, and we can just turn these into a float here and maybe even group them like that. Just so that in our heads, we're thinking, okay, we're doing float divide by float. It's a good idea to do this. You don't have to do this. This is also fine to just, remove these, make sure you're still doing order of operations, all that good stuff. Now we can click run and we can see what we get back from our results. And would you look at that? Nice. We get okay. And we got some skipped because it's going to say, hey, you got to wait till you click submit. That's where you're putting it all on the line. You got to get it right this time. So hopefully as the instructor, when I click submit, I still get this question correct. Boom. Wonderful. So that's basically what's going on here. That's just a little trick to note that only one of them has to be a float to do float division. C will figure that out and do it for you automatically. All right. Next lesson. Since we started doing some math, let's cover the rest of the operators, right? We got all the classics, plus, minus, star for multiplication, slash for division. If you're coming from Python, we still got the plus equals, minus equals, etc. But C does have, I would say, kind of two. They're kind of essential operators in a sense because they get used all the time. But at the same time, they're a little bit goofy, right? Writing plus to just mean x plus equals x, 1 or something like this. It's a little bit goofy. And basically, this is actually where C++ that comes from, but that's an aside, right? So we call this increment and decrement operators, right? And the tricky thing for these is that it's possible to use them both before and after a variable. So in postfix, right, or prefix. This one is the one that I would use. Just don't use prefix, okay? We'll talk about that in a sec. But postfix kind of makes sense because it's basically all right, you're going to get the value that was there before and then do the increment, okay? And the reason that this one is going to be useful is for for loops. So we'll get there in a sec. Prefix is it's changed and then the new value is used, and it's very confusing, okay? Because I don't know if it's just because I use postfix way more. So then I'm used to postfix. I'm well, that's just the one that it is. It's obviously right. How everyone says zero-based indexing is the best, but it only makes sense for C. This kind of thing, I don't know if it's just confusing because I mostly use postfix, but in general, my suggestion would be just write out the thing that you want. You know what I mean? You're just more likely to get it right if you write it out step by step than to try and do this move. But whatever. This is my walkthrough. If I want to get distracted telling you about postfix versus prefix, too bad. You know what I'm saying? If you don't like it, just buy the course and then go do it yourself, or just read it for yourself since it's free. Okay, so what are we doing? Complete the snake score function in exercise C. Snake laying is unique in that its toolchain gives developers project score, right? So what are we going to try and do? It says, hey, we're going to multiply the number of files by the number of commits to get the size factor. So I would say something like int size factor, and that's going to be, we said number of files, num files times num commits. Ooh, almost got me. I almost got myself, even though we did it in that order. Add the size factor to the number of contributors to the complexity factor. Int complexity factor is num contributors plus size factor. Multiply the complexity factor by the average bug criticality. For most of you, 100%, but that's besides the point. Criticality. Ooh, we're going to definitely need to do this in the run section because I don't want to lose my submit streak. And hopefully you spelled everything right. Oh. Yeah. Yep. Oh, yes. Let's go. Look at this. Sharpshooter spree. Next lesson. C, of course, also has if statements just like you'd expect, right? And they're pretty much the same format you'd expect. You use the word if, then parentheses required. So left parenthesis, some condition, right parenthesis, and then brackets for the body, just like we've been doing for basically everything else. It's also got else if, but really, it doesn't really, in a sense, sort of doesn't almost have else if. It does, but it's almost like you could just read it as else and then if, but that's whatever. So you can do else if, some new condition, and then the last one, else, doesn't require any condition here, right? And then that will run if none of the ones up here run. I feel like I have to mention this, even though it like hurt me a little bit to put it in the course, which is like you can write an if statement and everything on the same line, if it has no braces, will be considered the body. The only time I've ever seen this look kind of good is you go like if x greater than 10, return error or something like this, where you have like a return on the line. But is it really so much worse to just include the brackets and not get scuffed? Because I feel like what generally happens, right, is you can do something like this, if x greater than 10, and then whatever, you might do return 0. But then I promise you will do this at some point if you do this strategy. You'll say, oh, well, what is like printf x, and you're like this, and you want to do something like that. And then, you know what? This is no longer part of this. It's just bad, okay? It only works for the next statement. It only works. So just don't do that. Just always have the brackets, okay? For me, you can write out those 2 extra curly braces and say that one's for Tej every time. You can tweet at me. You can say that one's for Tej every time. That's great. But please do that. It's better and you'll have less bugs. So it's like, I'm just going to hide this. We don't even want to exist. Anyways, take a look at exercise H. Okay, cool. Get temperature status. Yup. Okay. What are our tests here? Get temperature status 50. Gets down too hot. Oh, right. Nice. And we're doing Fahrenheit, which is honestly, I'm just going to throw it out there. Fahrenheit is pretty good for living life. Okay. So what are we going to do? We're going to do, we're trying to make a function here, char star, get temperature. I'm honestly, okay. I hate to do this. I'm going to copy this. I hate to do it, but I can't. I'm not going to spell temperature right, and I'm going to choke. I'm going to choke bad. Int temp. So what are we going to do here? We're going to say something like if temp less than 70, return to cold. Okay, and we'll just return a static string, so that's fine. And then we can do else if temp more than 90, return to hot. And then we'll also do an else here, return just right. Okay. Since we have else here, that should be good. We'll click a run to make sure we've got that all going here. And looks good. We'll hit submit. And we don't need to do the too long because we're not returning a new line string, right? We're just returning the string itself. You can check the tests, right? And it just checks the different values. So that's it. And we can go on to the next one. That's if statements for C. Just like JavaScript, C also has a ternary operator, and it's basically like a mini if statement, right? So here's like the condition, and then here's the first block, and here's the second block. The nice thing, though, is that for these kind of ternary expressions, you can assign them to a value, right? Because like in C, ifs are statements, not expressions. You couldn't put an if like right here, right? That wouldn't work. It wouldn't work to just put an if right here. So this lets you get the result of those kinds of things, right? So this is like a one-line max function here. The question mark denotes when we're done with our expression. Here's your first value, and then you have a colon. Here's the falsy value. So I think, they're okay for like a few scenarios. Maybe something like this can make sense, but it just feels like one of those things where you end up writing like one ternary, then you've got two, and now you've got like everyone uses them everywhere, and suddenly they're writing like React in your C somehow. You say that's not what we want. So they're okay, but just don't overuse them. Basically, that's my suggestion. So the question is, what's the result of 1 equals 0, T or F? Well, 1 is not equal to 0. Pretty good at math myself. I do actually have a math major. So it's not going to be the truthy value. It'll be the falsy value. So we can click F and move on. So we're going to talk about the size of different types in C. This is going to be maybe something that, like, if you're used to just writing JavaScript, Python, this kind of thing, you're not normally thinking about, but it's really important to start considering it in C because it's going to start unlocking sort of the pieces for us to understand how C is allocating, using, and referencing memory. So we got to start here. One thing to note, though, that's kind of goofy is in C, not all types are always guaranteed to be the same size. Like int just means like whatever the int size is for that particular CPU. Lots of times that's 32. Maybe it's 64. Maybe it's 8 if you're doing some embedded thing. Like, I don't know. I can't actually tell you like what it's going to be ahead of time. So you actually have to use the size of operator to find that out. In general, though, this is kind of like, we can talk about a few of these. Char, it's always 1 byte. That one is good. That's like pretty important, actually. Then we have floats. Floats are, I think, almost always 4 bytes, and they're a very low precision, but it's okay. Floating point number. Then we have double, which is 8 bytes, and that's much better if you're gonna do like actual floating point math. You probably want to use doubles. I think it's literally called double because it has double the amount of bytes as the first float. It just seems like such a programmer thing to do, does it not? So anyways, you have to actually check the size of on your particular like CPU that you're running to see, but it gives you sort of an idea. So the size of data type same on every computer, false. Okay, that's what you got to remember from this lesson, false. Like I mentioned, C does give us a way, though, to actually check that size, and that's the size of operator. So you can use size of, and it kind of looks like a function. Like when you run it like this, it kind of looks like a function. It's actually an operator, which was a bit of a surprise to me. But what we can do is we can check the type, check individual types, and we'll be able to see the size for each of them. So oddly enough, ZU is the size of result there. And so in this case, what we're going to do is we just want to add to each of these different types. We want to print out each of their results. So we'll add those right here. And we can run these to see sort of what the result's going to be. And we want to do this in order. So we're going to do the same thing here. Printf size of, and we can do bool. And then we can go, did I want to make these exactly line up like this? I actually don't know. It seems like we want to because it looks way better when we do this. And then let's do this, and we'll do bool, and we'll say int. And then we'll change this, and we'll go s int, and we'll say float. And then we'll go per float. Dang, I didn't think about that. I should have thought of that. I didn't think of it, but I should have thought of that. S float double. Okay. And then we've got, that's all of them. Oh, nice. Okay. So let's see what that looks like when we run all of those. It should look correct here, I think. And so we can go ahead and give that a submit. And I think that should give us exactly, no, my streak. That's okay. Were we not supposed to put the equals inside all of them? Run this to see the size of char. Oh, classic. I didn't do that. I didn't do it. I didn't have char. I didn't have char like it said to do. What a mistake. What a mistake. That's okay though. I have char on both of these. I wasn't paying attention. Dang it. Okay. Okay, so we actually have, I just missed that we need to put size T here, so we can add that, and then we can go ahead and submit to get the correct sizes for each. The important part for this one, right, is that what we get here is we see char and bool are just 1, and then we have ints are 4, floats are 4, doubles are 8, and our size T is 4. That's because we're running this literally in your browser, so it's like WASM, you'd get a different result if you ran this from the command line. So that's our size of info there. Now on to another feature that should be pretty familiar to you, for loops. So in C, we have for loops. They are a little bit different though than maybe some of the other languages that you're used to. There's no sort of like iterator pattern or way to just directly iterate over a collection of elements. Instead, what we have are basically 3 main parts for a C loop: initialization, condition, and some final expression. And like I said, there's no way to just do for car and cars. We can't do that. The technology did not exist at the time. So what does it actually look like? We have our for and then mandatory parenthesis, okay? And then we have some initialization. So this runs once at the beginning. Then we have a condition that's checked at every iteration. And then we have something that we do at the end of the loop. And so here's what we've got going on. So we've got something like int I equals 0, right? We're going to set the index equals to 0. Then we're going to have some condition, right? And if it's true, then we're going to execute what's in the body. That's this loop body here. And if it's false, then we will stop doing the loop. And this is usually checking something maybe like, hey, is this less than the length of some array or list? And then we have some final expression, which is executed at the end of the loop body. And the loop body is down here. So in this example, we have int I equals 0, right? So that's the first thing that happens. Then we check every time, hey, is I less than 5? And then while that's true, right, we're going to say, we're going to increment I at the end of the expression, which you can kind of think of like putting this and like bringing it and putting it right down here, right? That's kind of like it's getting executed at the end of the loop. So we want to do something. We want to implement print numbers prototyped in exercise H. So it says print numbers start and end. And we're going to check and make sure that that all works. So we'll do void print numbers, and we have int start and int end. And that's going to look something like 4. Now we need to say, all right, what are we going to put here? Well, we need to put what we're going to start, right? So we can say I is start. That's our initialization. That's what we're going to start with. Say I less than end, and then we'll say I plus plus. And then we'll say printf, and we'll just do something like %d new line and I. Make sure that that's actually what we're expecting in the tests here. So printing from this to this, going here, print numbers, start and end, 42. Yeah. Prints all the numbers in that range, inclusive. Hey, close. Let's check that out, shall we? So we should see our, 42, so send it. Nice, there we go, perfect, right? So initialization, condition, final expression. While loops are almost exactly the same, except that instead of having an initialization and some post condition, it just says while this thing is true, and that's it. So while I less than 5, this is basically like the unrolled version of the one that we had before. Okay, so now what we're going to do though is we're going to do something int start and end, but we're going to print them in reverse. So we can do int print numbers numbers reverse int start int end. Okay, and we'll go while let's say int I is end, while I greater than or equal to start, then we're going to printf this this number with I. And then we'll do I minus minus because we're going to subtract from it each time because we're going to go from the beginning to the end. Oh, and I just realized that needs to be void. Okay, let's, we'll give that a go. See what happens. Oh, it actually says start is going to be 20 and 4. Okay, nice. I didn't realize. My bad. I should have read that a little bit better. We can do that maybe, and that should work. I kind of figured we would still do start and end the other way around, but you know what it is. It's good. Okay, so that's while loops. They're basically just like for loops. The last kind of construct we're going to talk about here are do while loops, and they're basically like a while loop, except you always execute the loop at least once. So when you see it, you'll see a do, and then some block, and then a condition. The reason it's structured like this is because it's going to do this, and then it's going to check this condition. If it's true, it will do it again and then check the condition. But if it's false, then it will quit. This lets you write a few. So here's a few examples, just like we've been talking about. You know, we're going to do this and then we're going to check that. That's great and all. This one will still print once because 100 is greater than 5, but it does the do anyways. So that part's important. The main reason I bring this up is because you'll definitely see do while loops in macros. There's a few cases where maybe some algorithms, it's a little nicer to do while. But basically, there's a little trick that we can do where we can put an entire block of code inside of one like expression, basically, or one statement by putting them inside of here and doing a do and a while. And that makes sure that nothing gets escaped from the macro. This is I would say probably more of like an advanced C feature, but if you're poking around at some C code, you'll definitely see macros sort of set up like this, because macros in C are literally text replacement. There's no like concept of hygienic macros or anything, if those things mean anything to you. So in this case, our assignment is basically we got to take what we've got here, move it to do, and then while this guy here like this. And let's go ahead and see if we wrote everything we needed. Oh, and I forgot a semicolon. My fault. And so that should let us get printing 1 to 5. That should be great. And there we go. Okay, so that's do while loops. The last thing we're going to talk about in our first chapter of C Basics are header guards and this pragma once. So we've seen that we're using header files throughout our code, right? And it declares the specification. But remember, C's strategy for doing stuff is like, let's directly just copy it in. So when we do like pound include, it just literally puts the contents of that file into the top of our file. Now, what you're thinking is that doesn't seem like it could cause any problems. Well, no, it definitely can cause some problems. And the one that you'd run into most often is if two files include the same header and they're included somewhere else, you're going to end up with redefinitions of functions or constants or whatever. And C doesn't like when you define something twice. It doesn't know which one it would pick, so you get an error. So the way that we solve this, the easiest way is to just use this thing called pragma once. And most compilers support this these days. And you can just put this at the top of a header file and it just you don't have to worry too much about how it does it, but like magically make sure that this header file only gets included once in our like program, so that we don't have to worry about those multiple redefinitions. The like older way that works, I would say probably like in a sense more reliably, like it would work on older compilers, is this header guard way. But this is the one that you're going to see. So most of the time at the top of header files, you're going to see this bang pragma once, or I mean pound pragma once. And so that's what's there. And it really is just about avoiding redefinition errors. It doesn't make anything faster or generating functions or anything like that. It's just about making sure that we don't include things multiple times and get errors. Structs in C are similar to classes or objects in Python or JavaScript, but they are a bit simpler. There aren't any concepts of things like inheritance or class methods or static variables, nothing like that. Instead, structs are simply a way to group multiple fields or data points, so you could sort of think of them out, and put them all into one object, right? So they get to be moved around and stored together. This is really useful because instead of typing 35 separate variables to a function, you can put some of those variables, logically group them into a struct and pass them around together. This is the same reason why you often would make something like a data class in Python or just a simple object in JavaScript. They are similar to objects as well in that they have a list of fields, but as I mentioned, they don't have any methods. They're only data. They have no behavior. And you can access the fields of a struct with the dot operator, or if you have a pointer to the struct, then you can access them with the arrow operator, which is really a dash and, like greater than thing. And if you have ligatures, then it looks cool like a real arrow. That's kind of my preference. But one thing that is different than what you might expect from Python or JavaScript is that the order that you define the fields actually matters in terms of the size and the layout of memory. When we make a struct, what we're really doing is we're telling C, I have several different pieces of data. I'd like you to put them next to each other in memory, and I'd like to operate on that memory as sort of like a block. Right? And that block can be bigger or smaller depending on how we lay out the data. Now, in other languages, you don't always have to think about this, but in C, you're tending to write things where you need to really crank out the last bit of performance. Really, everything in C, when we're talking about data, is just a bunch of bytes in a row. And our program is the one instructing the computer how to and where to access those bytes. C is really, in a way, a language of describing data and then what we want to do with that data. It doesn't have other ideas like encapsulation and methods and all of this other stuff that sort of hides away everything that we're doing. All right, what a great video. So well explained. And Stas, of course, did awesome editing. Maybe he'll even give himself a shout out right here. Anyways, so far, all we've seen in C are basically non-collection, right? They're like just atomic types, right? They're just one thing in C. But that makes things really annoying. What if you want to do something like, represent points in some 3D space, right? You're really going to have a distance function that always has to take every single point by itself? That seems pretty annoying. And also, then we run into a new problem here, which is we can't just write like int or something like this to say we're going to return 3 ints. That's not a thing. We can't do that in C. So we need to have something like a struct, right? And struct basically is we're going to say struct, the name of the struct, the opening parenthesis, then a list of type field, okay? So what we're going to do here is we're going to make ourselves a coordinate, and we just need to make this compile. You can see we use an X, Y, and Z for coordinate, and we're setting them all to ints. So when we first run this, it's going to say something probably like, hey, I don't know what C.X is. That doesn't work for me at all. So we can just go int X, int Y, and int Z. And if we submit this, now we've created a struct, we've given it the fields that we need, and all of our code can now pass. That's the very basics of structs, is type, name, semicolon, type name, semicolon, etc. Okay, great. So we can define a struct, but how do we actually make them? What's the syntax for it, right? So if we consider something like we've got a struct city and we've got name, lat, and lon, the easiest and simplest way is we can initialize all the values to 0 by just doing something like struct city C, curly brace, and then 0. This will set all of the things to the 0 value, which is basically like filling it all with zeros. We can also do a positional initializer, right? So in this case, we had name, lat, and long in order here with a character array, right? A string and an int and an int. So you'll see we do San Francisco and then the lat and long San Francisco. I think this is the best way. I think it's way less likely to come and shoot you in the foot later, which is doing designated initializers, which is basically a fancy way of saying like, we can do dot like field name equals value. And the reason it has dots here is because it's like you're accessing the struct, right? So you access the struct by doing like dot name. So you put dot name here. At least that's how I remember it. And then, sort of conversely, the way that we can access the fields is just by doing dot and then the name, and we can set those values here as well. This way is okay to do, but this is definitely the best one. Designated initializers gets a +1. That's the way you should write it. So the way that we would write this here is we could go struct coordinate C is, and then just like we're going back here, right? We can say dot X equals X dot dot Y equals Y and dot Z equals Z, right? And then we'll do this, and then we can return C. So that's a pretty easy way to do that. We can run to make sure we didn't leave any extra typos inside of here. And then we can go ahead and submit and do the designated initializers. That's a much simpler way to be thinking about how you write these. The other main thing is like, it's really scary if one day someone switches the order of these and you did positional, you'll never figure that out. That's just going to be a nightmare. So that's how you actually make structs. But not only can we create them, right, we can also return them, and we can also modify the values as well. So what we're going to do here is we're going to create a new coordinate, right? And then we're also going to add a scale coordinate, struct coordinate scale coordinate, right? And that's going to be, it's going to take in some coordinate value here, right? We can see test scale. It takes in a coordinate C right here. So we're going to go, that's going to take struct coordinate C and some int scale. Or do we do a float? Oh, we just do ints. Great. So now what we can do is we can take this and we go back to here. And oh yeah, right there, factor. Okay. And so now what we can do is we can make ourselves coordinate scaled, and we'll go ahead and make that our value here. Now, what's interesting here is we actually don't have to do this necessarily. We're going to get into this later because this value is actually copied into the function. So we could modify it freely, but for now, let's not do that just because you don't actually know that yet. I mean, now you do because I just said, but too bad. We're doing it this way, and you can't stop me. Even Lane can't stop me unless he AI doctors this video to make it so that I didn't do this anymore, and you can't hear me ranting while I write the rest of these here and then return scaled. Okay, I don't know. Maybe Lane would do that to me. I hope not. We're going to submit anyways right now and stop this rant and then go to the next lesson. At this point, though, you're probably thinking, like, do I really have to type struct and then this big name every single time? Well, how can I make it so that I can just type the name of the thing like you would ints or other types? Well, that's because coordinate itself is not a type. It's a struct coordinate is its type. So what we can do is we can use the typedef keyword where we can basically put typedef before, and then we have a struct, and then we have the new type name. A convention that I've picked up from writing in NeoVim and some other places is to underscore T at the end of these. Some people don't like that because technically it's reserved by POSIX, but okay, they're not going to make a pastry T type. I don't know what to tell you. Like, it'll be okay. If it is, then you just go replace all the pastry T's in your code base with something else. I think it looks nice, and I like that it kind of like looks the same as all the other ones. There's a few other ways that you can do that, but that's just fine. So in this one, we're going to go over to our coord H here, and we're going to add a typedef here, and then we'll say coordinate T. Okay, so now we just get this one word that we're going to use here, and we can change all of these to just be coordinate T like this, and we can do that for here as well, and we can do it here, and also as well in inside of functions arguments. So that's nice. So this, I mean, to me, I don't know if it matters to you, but to me, I just find this much more appealing. It just looks like a regular type like everything else, which makes me happy. Oh, we should submit this. But I'm sure we got it. You know what I mean? I'm sure we got it. Okay, that's it. Next up. Next episode. Next lesson. Let's go. As we saw before when we were investigating some of like the built-in or standard types, we saw that size of can be used to tell us the size of something. And like the joke I made in, here is for once programmers actually thought of a name that was helpful, which is true. Size of really does tell you the size of things. We can even use size of though to tell us what size types are. So this can tell us what's going on. Structs are basically like the thing you should think of them is they're a way to talk about or name different like relative locations within a block of memory, which is probably confusing, but you just think about it like this. We saw earlier that at least for our platform on boot, ints are 4 bytes wide. So we have field X and that takes up 4 bytes. And then the next 4 bytes will be field Y. And then the next 4 bytes will be field Z. So this struct is a 12-byte struct with each of these here. You can have different things where you have chars, ints, and doubles hidden inside of here. And one thing that's important to know so that we're just on the same page, we won't like exploit this very much in the course, but it's important to recognize that C, like, because first initial here is a char, it's going to give some padding here because it wants things to align on what are called like word boundaries or approximately word boundaries, which just means that accessing age, it's actually faster for it to be on a 4-byte aligned address than it would be to start here. And so it actually moves this all the way over to this section. There's some other stuff. There's a bunch of CPU things. We don't have to get into it, but you should know that this padding is happening and that C actually cares about the ordering that you lay out a struct. So size of struct is always the same value as the sum of the size of fields? No, because we can have padding. So just to wrap up this idea of padding, we're going to give an example. We already talked about how they're contiguously laid out and they can vary in size. They also can vary in size depending on the compiler itself. Some compilers might choose to do more or less padding. It's very like dependent on a lot of different things. But in general, it's sort of an easy way if you're trying to optimize this is order your fields from largest to smallest, and that should usually minimize padding. So if we rearrange these to be smallest to largest, we see an int is bigger than chars, so we can move this up here. A char star name is also bigger than those, and it's, I think on this one, the same size as an int. So ideally, now when we run our test, it should say that the size is 16 in our online playground. We'll give this a run. And if we actually added these up, we would think, okay, char star, that's 4. We saw that pointers are 4. This is 8, and then this makes 12. So it seems like it should only be 13, 14. But remember the padding that we talked about in the previous episode, that's going to get added to the end of this struct to sort of round out what we've got. We could even add char useless and char something here. And if we like resubmitted this again, it's still going to work because that was where the padding was initially. All right, chapter 3. We're now going to begin talking about pointers. Don't worry. It's going to make sense and we're going to have fun, okay? So just bear with me. We're going to have a good time here, okay? So we are going to be doing a bit of hand waving in this section because computers are, approximately infinitely more times complicated than what we can explain in one markdown file, okay? So just like bear with me on this part too, okay? It's going to be a little more complicated than that in real life, but this should give you a good mental model, okay? So the first thing is, as we're thinking about this, we should be thinking variables are human readable names that refer to some data in memory, right? So when we see a variable name, we're saying, that's really like, it's just telling me where to grab some data in a way that's actually useful, right? Like how we use addresses instead of latitude and longitude for people's houses, right? And that memory is really a big array of bytes, and that data is stored in like a big array. Okay, that's it. That's all we have. That's all computers have. It's just zeros and ones in a row. Okay, that's all we have available to us until quantum computing comes and takes away our jobs. A variable is a human readable index, right? So we're just sort of saying like teej, right, points to these 4 bytes here, teej, right? And then teej dev would be 1, 2, 3, 4, 5, 6, 7, 8. Right, that seems good. And those would be next to each other, right? These might actually have null terminators and stuff. We'll get to that later. So in C, you can ask C, hey, where is this variable's address, or what is the variable's address, by using the address of operator, which is the ampersand. So to say the address of age is, we can do %p, right, to print a pointer. And we can use the address of age. So that's what this operator does. It says, give me the address of that. Okay. So what are we doing here? The size of adder function accepts a long, which is a really big number, or could be, as input, and returns the size of the address. There's a bug. Memory address thing should always be 4 bytes long. Fix the function so that it returns the size of i's address, not value. So we need to get the address of I, which should be here. Let's try and give that a little run and see what we're seeing here. And it says, okay, now we're getting the right kind of thing. So that looks pretty good. We can give that a run. So we used our address of operator to do that. Okay, so that's sort of that first thing that we're starting to understand when we're accessing memory. But since we said that we can get the address of something, what do we really mean? You know, it's not like an address of like a mailing address, 1234 Elm Street or something like this, right? It's literally just a number. It's the offset from the beginning of memory. Now, once again, there's virtual memory, there's all this other stuff going on, but you should just really think about it as like the index into the array of bytes where we can find this thing. Usually this number is written in hex because they're really big. And so this shortens that a little bit. And there's some other reasons because like bytes are usually 4, 8. There's some power of 2. So like hex is nice, better than 10. So we use hex. So this is what you're going to see when it's printed is some hex value like this. And so which one looks most like a memory address? Boom, the one in hexadecimal. And like I was alluding to before, we don't actually get just direct access to RAM in our programs. That would be kind of a bad plan. Instead, we get virtual memory. So the real physical memory is like the physical sticks that you have. Then the operating system has some management it's sort of associated with those things. It does a bunch of work there. And then we have a program, and when it runs, it's given some process which has its own chunk of virtual memory requested by the operating system. And so then that's sort of like the virtual memory that we're actually working with. You can think about it like this. Our program asks the operating system, yo, dude, can I have a little bit of memory, please? And it says, I'll check yeah, I do have some, and then it gives it back, and then that's the virtual memory that we have associated with our program. There's a bunch of reasons for this. You don't want programs being able to talk to each other's memory. You don't want to be able to access like, I wonder if I start scrolling through here, this memory, if I'll see any passwords, or, oh, I'm going to be able to execute instructions in a different program. Bad plan. Happens all the time in C, but it's a bad plan. It also makes it a lot simpler. Like, you don't have to write custom drivers yourself for everybody's computer. Instead, you just write stuff in C that requests memory and gets it back. So that's quite helpful. And then this operating system can do a bunch of stuff like, oh, this process is getting a bunch of memory. Let's give them a big chunk, blah, blah, blah. The operating system can manage those. So that's sort of the basics of what's going on there. The really like sort of level 2 kind of mental model there is that you're not actually getting like an address in RAM. You're getting some address specific for your process that was given to you by the operating system. So the memory addresses your code sees are the same in physical address in RAM. It's not necessarily never, because like you might get lucky and they might happen to be the same thing, but basically you should just think basically never, because they're in a virtual address space instead.
Pointers. Anyone who tells you that they're very hard has skill issues. We're going to walk through why. What you need to remember here is that pointers are actually just a value that tells you the address of another value. Consider int x equals 5. In this simple statement, what we're going to start with here is that we have some variable x, and it's going to have some address in memory. We're going to just make one up, okay? It's not a huge deal. But what we're going to show throughout this section is think of pointers as just addresses to data, and you're going to be all right. We start with our first one, x. We give it some long, big address, which is similar to the thing you'll see printed out when you print out pointers in these lessons. And then we give it a value, like 5. Now, when we create another value, like y, and we say that is equal to x, what we're actually doing is copying the data of what was ever at x and putting that into y. Remember, this is a copy. So if we do something like update the value of x, what's going to happen to the value of y? Nothing, okay? Instead, what we'll have is only x will get updated. Now, here's where we're going to start introducing pointers. We introduce this by saying int star and then a name. So this is saying the type of this is a pointer to integers, and we're going to point it to the address of x. We do that with a fancy ampersand. So what we have though is this pointer, and it's at some other address in memory, but its value is actually that original address of x that we're talking about. So you should just think in your brain, what we're doing is I'm setting that value to here. We've copied the value of the address. This is like if I give you my address is 1234 Sesame Street, we're going to copy that in. Now, when we do something like dereference that pointer, which is saying, hey, I'd like to get the value out of that pointer, and we set it into Z, we create a new name at a new address, and we set that to a new value. Once again, very important, this is a copy operation. Okay, this means that we cannot just say that these things are going to be in sync forever, but instead that it is a copy. Just the same as when we copied the value from x into y. However, now what's going to happen is if we say, hey, let's change what's in the memory location that the pointer points to. Well, we go back to our table and we refer there and we say, aha, I need to update my value of x. So what we have is still just copying values into new locations in memory. It's just that sometimes the value itself is an address. So after that wonderful video, our next stop is just learning some of the basics of the syntax. We've already learned the address of, but now we're going to use how to declare a pointer. We've already done this with char star, right? And so here we go. We've got int star, which means that it's a pointer to age here, and we get the address of age to set it as its value. So learning about pointers is easy. When Tej writes the course material, obviously that's better be the right answer. Okay, was worried Lane changed that one on me, but we're safe for now. Now we're coming to some key information. We're going to show the first reason why we need pointers. If you think about something in Python, right, you make a class, you want to update the class, you call the function that updates the class, it mutates it. Great. We've already seen that we can mutate things in C, but we're about to see something a little bit
more confusing than that, right? We're going to make something here where we try and update a coordinate, and we can do cord.x equals new x, okay? So we're going to update this value. And the thing we're going to see, we're going to be a little bit surprised by, is that this doesn't actually change the original coordinate value. Why does that happen? Well, the reason is values here, arguments, parameters, whatever you like to call them, they are passed as copies. So C copies coordinate into coordinate update X. So if it copies the data, puts it here, so we've got our original and we have our new one, we update this one, we didn't change anything about the original. So instead we could do something like this where we could say cord.x is new x and then return cord like this. So here, should let us pass both of these tests because now we're going to be updating a new copied value and then returning that copied value that is updated. So when we check our tests and we're looking at this, we'll see this first one, the new coordinate, it doesn't change. It never changes because we're only changing a copy inside the function. This is going to be really important. You got to lock that piece of memory in. Function, parameters, or arguments are passed by copying the value into the function. And so now we have been able to declare a pointer and to get the address of something, but how do we get the value back out of a pointer? Well, what we do is we call dereference pointers. And so oftentimes we have a pointer, but we want to actually get the data inside. So we use the asterisk operator to do that. And so basically what we see here is we have some int value at pointer equals, and we're going to dereference the pointer. This is basically like find where the address is and get that value. Okay, it's like going to somebody's house to like get something out of the house, right? We're going to this address and then we can get the thing out of it, okay? So this says fix the change file type function both in C and H files, and it should accept a pointer to the code file. So that means we want to say this because that's a pointer. And then now we need to go over to here and we need to say, okay, what we're going to do is we're going to dereference the pointer into a code file T struct. So we need to go like this and this. So now we get a new one here. Change the file type to the provided new file type value. Yep, we do that. And then return the updated code file struct. So that's what we do. So if we run this now, because that's what was already there, right? We run this now, I believe we should be getting the correct answer here. Yep, and we get all okay so far, and we can click submit just to make sure that everything worked out just fine there. Great. So just to review, we changed this to a pointer, so we have to add the star in front of it. Then when we sort of like get the value back, we have to dereference it. I do think there's a little bit of confusion why we have to use star in both of these, but such is C. What can I say? There's a few tricks if you think about this sort of being like more or less like the value itself, right, is F. And so we're saying this one says, I'm going to make a pointer to you. That's like on the left side. You can do on the right side to like undo that operation, almost like, you know, divide both sides by asterisk and you get the same thing. I don't know. You just have to sort of think in your own head how it makes the most sense for you. But I usually like just saying it out loud in my head what I'm writing so that I can do it right where I say code file T pointer to F. And in this case, I say code file new F equals dereference of F. So if you just like say it out loud, you can remember which order you're going for each operation. There is sort of one trick though that goes with this, which is we're going to introduce the arrow operator. The arrow operator is like dot, but it operates only on pointers. And so really what the arrow operator is, when we do something like pointer to point with an arrow to X, that's really the same thing as like dereference and then dot X. It's just nice because you get to do a lot less parentheses and a lot less order of operation stuff because you can continue just using the error over and over. So this one is good, pointer to field. This one is good because it's the same. This one is not good because the star has a different precedence and will be in trouble that way. So that's the one that doesn't match with our other options. We'll be using the arrow operator quite a bit in this course. And now we finally have enough info to start talking about what are arrays in C. So they're a little bit like lists in Python, but they're a lot lower level, and there's a few distinct things. So the first is that they are fixed size. When we see something like this means there's 200 elements and 200 elements only. We cannot just make that bigger or smaller. We'll have ways to reallocate stuff later, but this one is fixed size. They're indexed by integers and they start at 0, but they can only hold elements of the same type. There's no like int or string or coordinate arrays. We can't do that. You can't just put anything you want in a list. It can only be lists of one thing. And they're all stored in contiguous memory, just like structs. So here's an example integer array, right? It just goes 1, 2, 3, 4, 5. Notice this one is at index 0. And to iterate over it, we cannot do 4x in list. No. Cannot do. Instead, we have to do just like we were showing before with our sort of like, hey, here's how we do for loops, initialization, condition, final. We can do that same thing. And then we can get the sort of experience that we're expecting. There's just no iterator style for loop inside of them. And arrays are mutable by default, so we can update values by doing array index equals value, just like you expect from like other languages, basically, right? So that lets us update some values. We print it. We'll get the new things. So complete the update file function. The file data array is a large 200 integer array representing a snake length source file. Each integer array represents a special piece of data. Index 1 is the number of lines. So we can go something like int lines is file data 1, index 1. Okay. I'm assuming we're saying index 1. I'll just double check for when we say that. Yeah, okay, 1 and 100. Okay. 2 is the file type. 199 is always 0. Update the function so that it overwrites index 1 and 2 with the provided values and ensure that index 199 is always 0. So let's go ahead and go. We want to say, not this. We want to say file data 1 is new file type. Nope, that's actually 2. Nice. And file data 1 is new num lines, right? And then we're going to ensure 199 is always 0 by just going, we can just say file data 199 is 0, like this. So let's run that and see if that comes out the way we're expecting there. That's just sort of ensuring that that's always 0. So let's hit it with the submit and bada boom, bada bing. Wonderful. Everything passes. So we're just accessing these and writing to them just the way you normally would, you'd expect from like something like Python. In C, arrays and pointers are closely related. So an array acts basically like the name of the pointers to the first element in the array. So array indexing and pointer arithmetic, basically same. There's a little bit of goofiness because arrays can lose some of their information once we go through functions. They kind of get like downgraded or downcasted into just a regular pointer, but that's okay. We'll cover that as it comes up. So if we think about it, here's where we declared our numbers. We can also say that numbers pointer is just a star, which points to the beginning of numbers. And accessing element, notice we didn't have to do address. This is just saying this is a pointer. So we kind of like downcast it, if you will, or it implicitly converts it. So now we can do numbers too. That's actually the same thing as doing let's dereference numbers plus 2. So this is like saying get the second index. It takes into account the width of the data that you're using to move you to the right spot. And in fact, we can just write this as normal arithmetic by adding numbers and dereferencing them as you would expect. And so basically, like you should just be thinking numbers plus 0. That's the same thing as numbers 0 here, right? So these are basically getting expanded out into dereference, basically pointer plus the index, okay? Just like we said here, like this. And so when we check some example code and we look at these, right, we can see how numbers 2, this outputs 3. These two things are the same. So when we go to which two statements are the same, 4 and 8, no. 4 and 4, that seems good. 4 and 2, that seems good. No, that one's crazy. So this is our good answer here, okay? And so here's where we continue on down this path of arrays where we're thinking, okay, a multi-byte array. So we're sort of thinking like, okay, sure, TJ, you showed me just before how an array like of integers, that kind of makes sense. Each one gets its own address, they're one after another. But what happens when we go back to our coordinate struct? This takes up like more space, right? We've got 3 integers here. If we had an array of 3 of them, then this would take, we decided 12 earlier. So this takes 12 bytes, and this takes 12 bytes, and this takes 12 bytes. So when we print out the values of the second element in the array, right, with index 1 here, we get 4, 5, 6. Or we can do our same pointer arithmetic like we were saying before. Not too exciting. The memory layout, though, is just like we were talking about here, where our very beginning of the array points to the very first field, which is 1, and that's offset 0, right? And the Y value is the next 4 bytes, and the Z value is 8. And then we repeat the same pattern for each one in the array. And so we're going to talk a little bit about maybe the pointer arithmetic, but the main idea here is C knows how to calculate this offset to move to the next offset in the array because it knows what the type of the array is. This is why we had said before, C only has homogeneous arrays, right? It only has arrays of the same type so that it can know how far it needs to offset to get to the next element in the array. So when we consider the question, 8 integers in fields, we've been doing an integer is 4 bytes in this course, so that's 32. So the 5th element is basically there's 4 elements before. So 4 times 32 is 100, right? And 30, whatever, 34. Yeah, right. And then now we can do times, we need to add the C. So that's 0, 1, 2 to get to C. So 136 is our final answer after we add that up together. So that's what's kind of going on there is you could just think about multiplying by the size times how far of an offset we are, plus the offset of any of the given indexes inside of the list. And to really illustrate this point, we can do something that I would generally not recommend doing, but just shows you what's kind of going on under the hood. If we think back about this coordinates where we have 3 of these in a row and each of them are integers, we can actually just cast points to say, I actually don't have coordinates here anymore. I just have integers. And that will work because we're telling C, ignore what you know about the types, instead do mine instead. And we can iterate over all of the known numbers in the array and just print off 5, 4, 1, 7, 3, 2, 9, 6, 8, which 5, 4, 1, 7, 3, 2, 9, 6, 8. Those are the coordinates that we had in order. So in this case, we need to make it so that this only prints up to how many settings we actually have. So if we look at our example, we see we've got about 10 of these graphics arrays right here, each with a number inside FPS, height, and weight. So FPS, height, and width, not weight. And we only have 10 of them. So what we really want to say here is this is 10. We can put this in parentheses just to illustrate my point, times size of, right? And we can say G settings like this, okay? So if we, graphics T like this, right? Because we want to get the size of this. So initially that said, size of won't work. We don't want to do size of because that'll be times 4. That's how many integers we have. We just look at how many integers we have, 1, 2, 3. And so we want to say, okay, well, that's going to be 3. So 30 instead of 60. When we submit this now, we'll actually get that we only print off the right number of these. If we had done some other number, we'll just start accessing memory that we don't know what's inside of, which is a common problem in C. And now we should just quickly talk about the fact that all pointers are the same size. Pointers are like an address, right? That's what we've been talking about. And so the address always has to fit in the same size of memory. And that depends on what kind of computer you have, like 64-bit. Okay, well then the pointer size is going to be 64 bits. Okay, so then when you do size of, you're going to get 64. Now, if that's not the case, if you're on some different kind of platform, you might get something like 4 instead of 64, right? So this tells us the size of these. So these are all the same size no matter what. All pointers are always the same size. But this is where we talk about pointers and arrays are slightly different, even though they're a little bit goofy sometimes. If you're operating on an array, not a pointer to a list of elements, right, but an array, and you do size of, C actually can still keep track of what the size of that array actually is. So the sizes are different for these because the array keeps track of its size until it's downcast into just a pointer. So blank have the same size on the same system, while blank may have different sizes. Pointers always have the same size, and arrays might be different. So as I mentioned, there is this concept of arrays to decaying to pointers. And what this really means is just that we can basically have an array and the compiler remembers how large that thing is. But as soon as we cast it into a pointer, we've lost that additional information, right? So they don't decay when we do like size of, they don't do it when we ask what the address is, and they don't when we initialize them. But more or less like every other situation that we do, they are going to decay. So in this assignment, we'll take a look at the main function. It declares an array of numbers core utilization that represents the CPU's utilization of each core on a system. So it has 8 elements. On line 12 and 13, it prints the size. Complete the core utils function to print size of core utilization in core utils function, size of core utilization in main in core utils func. Okay. So when we go to core utils func here, right? And when we go ahead and check that out, we don't have this function. We can just print basically the same thing here, right? Like this, size of core utilization, but now we're going to be in core utils func instead of in main. When we run this, we should get different sizes. Let me make sure I just copy pasted that, right? Yep. Okay, so here's where we can submit, and we'll just make sure that we got everything right. But we'll see what happens is it knows that it's 8 times 4 for int times 8 here, right? In this function here. But as soon as we pass it to here, it decays down to simply being a pointer. So that's what's going on when we talk about array decay in C. And now we can finally talk a little bit more clearly about strings in C. And so since the beginning, of course, we've just been doing basically string constants. That's kind of all we've been able to do. And while we've been doing that, I said, don't worry about char star or char star, if you will. And now we can finally understand what this is. This is basically special syntax for writing an array of single characters, okay? SSH will not shop for the best coffee. Good idea, good idea. So this is how we generally speaking represent text in C programs. And it's any number of characters followed by, at the very end, there's a null character. So like a 0, the 0 character, okay? And a pointer to the first element of the array. So that's how we represent a string. So strings are very simple in their construction, but sometimes more difficult to use because of some of the difficulties here. So like C strings don't store their length. Their length is determined by finding the first null character. And functions like strlen calculate that by walking over functions until we get to the null terminator. And this has caused a lot of security problems and a lot of bad pain points for people over the years. And it's good that other languages don't do this. Like I said, there's some historical reasons. Like you might want to keep, like, let's say you have one string and you want to get a substring of that, right? You don't have to allocate basically anything new to like get the pointer to the middle of that string. So there's some reasons why you might do it, but it's not good. It's going to cause you problems, which is fine. It's just the way that C is, but that's at least what's going on there. So we talked about a little bit before, you can declare strings in C either with the array style or with the pointer style. We usually just do this pointer style because it's basically the same. And the only difference where you might want to do something like this array style is when you want to pre-allocate, and we're going to talk about this on the stack, this many characters, right? So you're saying I can fit 50 characters into this string, right? That's what I want to do. And so we can cat, which just is like basically combine these two, concatenate, right? The second into the first. And now it's going to say Snake Lang as one character. There's some really important things here, which are like, you need to make sure that if you're going to concatenate two strings into each other, you have to have the strings like with enough like space to already do that. Otherwise, you're going to have buffer overflows and a lot of problems. But we'll encounter that as we go. And so basically, we get Snake, we get our null character, and then we have a bunch of stuff we don't know, and then we get to the end. The second one just looks like LANG, bang, and then this, right? It doesn't have any extra characters afterwards because we didn't pre-allocate 50. And once we stir cat it, we're going to get our snake, and then it's going to move the null character over to here, and then we have no idea what the rest of this looks like, and that's totally fine. So Snake lane, in this case, what we're going to do is we're going to write a concat strings function just to sort of get the idea of what's going on here and see what's happening, right? And we're not going to use strcat because that's cheating. So how does this work? We're going to basically, in this case, we're not going to worry about the case of like giving you two strings where the lengths don't work. We're just going to assume that they've done that correctly. And we're going to cat these together to get two strings and then make sure that it works. So let's go ahead and give this a try here. So the first thing we need to do is we need to find the null terminator. So we can say basically like, okay, where is that null terminator? Let's go something like int null terminator, something like this, is 0. And while, let's go, I think maybe even -1. My thought is like, while null terminator less than, actually we can just break out. We can just break out of this. We'll just go true and 0. And we can now go if, and we can go stir1 idx. So we'll need to do the idx, but really let's just, yeah, we can just call this idx. If this is, and we need to go like this, that's how you do null, then we're going to break. Okay, so now we found the null. Otherwise, we're going to increment this, okay? So as we're going through, this will eventually go here. And we could just even, if we wanted to right now, like as I'm thinking of how I would write this, we can just do something like printf found null at %d for %s, and we can say idx and stir1. So let's just sort of see when we run this. This obviously isn't going to be the right answer. We haven't done anything yet. Oh, we haven't included those. That's fine. We'll do while 1 for right now. That's okay. So this says, hey, we found null at 0 for okay, null at 5 for hello, right? And then 6 for, okay, so this looks good. This looks like we're finding the right spot here. Okay, so now what we need to do is we need to go for each of the characters here in string and iterate over strlen. We're not going to use strlen. I think that's probably cheating right now. We're not going to use strlen yet. I don't want to do it. So then what we're going to do is we're going to go character by character until we see the newest character. So let's go int. We can just say like, we'll go int stir2 pointer. And that can just be 0, right? And so then we can go while 1 here. And then what we can do with this is we can say if stir2 pointer, and we'll also do this, is equal to null, right? Then what are we going to do? Now we can just return. We're all done. We've copied everything that we need to. Actually, we probably should make sure that we copy it first. So let's go ahead and do something like stir1 idx equals, and we can go stir2 pointer, right? So we're going to copy this. We want, it's like, make sure to copy the null terminator. So that's why we put this before. We'll go idx and, oh no, we don't need to do that. We can go plus stir2 pointer like this. That's a little easier. And we'll just increment stir2 pointer like this, plus. And so if we do that, then we shouldn't need this print anymore. And we'll just try running this and see what we got. We'll see if we left anything there. Oh, right. We need to make sure that we're closing all of these. That's a good idea. Here, 22, line 22. I just didn't do that. Great. And okay, all of the ones passed there. So let's just walk through this again. We start at the beginning. We loop until we find a null, and then we break. Then we're going to loop from the beginning of the second one. And basically, we need to just copy over these values into the first string. And then when we get to the end of that second string, then we're all done. So that should work, I think. And nice, we got it right. Fortunately for us, though, we don't actually have to write all of these functions ourselves. We can actually use the string.h library, which has a bunch of these functions already. So there's stir copy, which copies a string. Stir copy is the destination and the source. We can do strcat, which is like the function we just make, which concatenates one string with another. Strlen gives us the length, which is very convenient. We wouldn't have had to do all of that looping in the last one to find those if we use that. Stir comp is like compares whether these two things sort next to each other. Stir n copy, the one that you really want to use, copies a specified number of characters from one string to another. And stir n cat, similar idea. Whenever you see this n here, it's sort of like number. It'll be the same string concatenate with just an n amount of bytes. Stir is the first occurrence of a character, so it's like string character. They really don't like letters. Okay, I don't know what to tell you. They don't like letters. I mean, to be fair, at the time that a bunch of these things are made, like bytes actually mattered in your source code. So it does make a little bit of sense, but it still is kind of laugh, isn't it? Stir is like stir char, except it just looks for the string. So complete the smart append function. It appends a source string to a destination text buffer struct. It's called a smart append because the destination buffer is fixed 64 bytes and it checks for available space, appends as much as possible, always ensures the buffer remains null terminated, and returns a status indicating whether the full append was possible. So if, I didn't even know bootdev does that. Nice job, Lane. I love this check mark action here. Okay, so here's the check. All right, we'll just walk through the steps. So if dest is null or source is null, then we're going to return 1 for failure. Okay. Nice. This I think will probably, we need to, then let's just say like return 0 down here for these scenarios. Okay. And I don't know why I just wrote or. Wow. I said it out loud. That's embarrassing a little. Okay. So it says, nice. So we get the first one. We've passed the first test. Excellent. Okay. So create a constant to represent the max buffer size of 64. So we can go const int buffer is 64, something like that. Get the length of the string of the source string using strlen. So int length is strlen source. Okay. Source len, maybe we'll say. Okay. Calculate the remaining space in the destination buffer. So let's go ahead and check this out. We have a size t length and our current character buffers. Okay. So that should be, don't forget to count for a null terminator. It doesn't count as part of the length. It doesn't count as part of the length. Got it. Okay. So in this case, what are we going to do? We're going to say int, let's say remaining space. We can type out the whole word. We're not professional C developers. We can use the whole word. So this should be dest dot. So this is 64 because that's the size of this, right? Minus the length, dest dot length minus 1 because we have to reserve the last spot for a null character. If the source string is larger than the remaining space, so let's go if source len greater than remaining space, then what are we going to do? Copy as much as we can into the destination buffer using stir n cat. Stir n cat, and it should be destination, which is dest dot, did we call it buffer? We did. Dest dot buffer. And then this is source, and this is remaining space. And then we need to say dest dot, we said length is 64 or 63. Do we say 63? We'll have to check, I guess. To the max size, which I believe that's going to be 63, right? Because we have to keep the last character. I'll double check when we're getting to the tests here. Well, let's see. What does it say here? Smart append, dest buffer here, dest length is 5. When we have our max one, yeah, it should be 63. That's what I thought. Nice. Okay, I remembered, right? Okay, and then return 1 because we didn't actually get to copy the whole thing. Then we can go else here, and we can move this up to here. We just want to go stir cat dest buffer source, and then that's it. Update the buffer length, which would be dest.length plus equals source length. Okay, well, I'm feeling okay about that. Why don't we give it a run? All right, these are actually pointers, which makes sense. So we need to change all of the spots where we said dot. We're going to change those to arrows. I forgot that we had this as a pointer. That makes sense. And I've got another length right here. Yeah, I do want to check actually if when we're doing this. Oh yeah, we want to change those because we're also doing that. I think it might be possible for us to go size of dest.buffer here. Let's actually check that. I want to try size of dest buffer because that is an array. Might actually know that. Oops, I said size, not size of. My bad. Nice. Okay, so this is like the better way, because if you changed this to be this, right, then it would be sad. And then I would change this as well to dest buffer -1. That's how that's in my mind how I would do it, right? And I think that should work just fine. Nice, great. So that's like if we changed this to not be 64 anymore, changed it to like 128 or something like that, then that would be okay, right? This would automatically update. So I like that. I like that style, which I think that's good. All right, next lesson. We've just got to cover one thing sort of quickly here, which is the idea that sometimes a struct might need to reference itself or use like recursively between two different spots. The first case is like a node, where a node might contain a reference to the next node. This doesn't always work, so sometimes you get some complaints like this. So the best thing so what you need to do here is you need to forward declare this. This is like saying, hey, compiler, I'm going to give you a struct at some point called node, and I'm going to type def it to node t. Just like when I do that later, that's going to be okay, right? So that lets us do that, but it will error if we try and use like the wrong name or something else. So it does some basic checks for us. So we can just say for this one where we want to make a forward declaration of snake object, which is coming soon, we should be able to just type that type def, which is exactly the same as we have here. And we're golden. And this is the other case that we might have, which could be if you had something like a computer and a person, they might sort of recursively reference each other, right? Where a person might have a computer and we want to keep who owns the computer here. And so we need to push these two things back and forth with each other. So here what we can do is we want to make employee T and department T, right? We're going to do something like this, where we have type def struct employee, and then we can do employee T like this, and we can go here and say department and department T. Okay, and then we can see what sort of values we have here. So we can have int ID, char star name, and then we probably have something like department T star. Did we call it dept? I don't know. Let's see. Department, nice. Department, right? And we need it to be a pointer because we don't want to allocate them inside of each other. That actually doesn't work anyways, because then the size isn't unknown. It's sort of like recursively there. So we need to make sure that we're sort of doing these as a reference to each other. And for department, we've got name and manager. So we have char star name, and we have employee T star employee. And the only thing we haven't done yet is we haven't actually added the type defs that we need right here. Oh, this is called manager, sorry. We need to add these actual type defs right here to say employee T. Otherwise, we would be in trouble because we never told it what we should call these, department T, like this. That's at least how I like to write it. And so with that, we should have all of our type things fixed now, and we're all set to go. All right, welcome to chapter 4. We are going to talk enums. Now, I already know Lane's getting salty in the banter here, okay? But I think the reason for that, and this is not cope, okay? I know, Stas, I don't know if Stas is going to make me look like a fool right now. He's going to put me in like children's daycare, like sitting in an ivory tower, typing away, writing white papers or something. But like Go should have enums and an actual enum keyword. Okay, I'm right about that. Go can still be a productive language, but they can be wrong about this. Rob Pike, call me, dude. I want to help you with this. Then I could write Go and I could stop trying to make OCamlSass ready. Anyways, back to what we're actually talking about here. Enums are basically just an enumerated list of possible values. In C, they're basically always just like a list of numbers with names, okay? That's basically all we've got going on. And in this case, you can see a lot of the same ideas that we had before. We have some sort of definition right here where we have an enum keyword, the name of the enum, and then the values. Monday, Taco Tuesday, nice. Wednesday, Thursday, Friday, Saturday, fun day, hoo-hoo, nice, right? And we can type def this again to give it days of week T. Okay, similar idea that we did before. And enums by default in C, this starts off as 0 and then it goes 1, 2, 3, 4, 5, 6 in this case, right? And you can use enum types then inside of different items, right? So it's like days of week, what day of the week it is. And you could use it without the alias as well. That's totally fine. So in this case, we're going to make a color T that has red, green, and blue in that order. So that's pretty easy. Type def enum colors. And we can go red, and then if you can refer back to here, it's commas to separate these because they're like a list. Green, whoops, and blue. They are case sensitive, by the way. And then we can go colors T. And I believe I typed everything right, and that should make it so that our tests are going to pass, which was basically just checking, hey, do we have red equals 0, green equals 1, blue equals 2, and they don't equal other things like this, right? So that's great. That's very basics of enums. But we do have a few other things that we can possibly do with enums. The first is that we can give them non-default values. So you can just say some enum equals the value that you actually wanted to set it to. And this is like a pretty common pattern. You'll see this for something like, hey, we have HTTP codes, we want to name them. Maybe not every single number is taken. We'd want to do something like that. Alternatively, right, you can actually start a default one here, and then you'll allow these to start incrementing right afterwards. So in this case, we can just update this to be red is 55. Whoops. And then we can say green is 176 and blue is 38. We can just write those in. And now the order doesn't even matter either. We can do blue, green, red, right? Because they're all specified. That doesn't actually make any difference now. So that allows us to set non-default values for enums. I think probably my favorite usage of enums are using them for switch statements, where you basically have a list of different possible options and then you handle them. It is not as good as pattern matching in OCaml. Yes, Lane, I'm still pitching OCaml. You just comment below, if you say we need an OCaml course. Anyways, so one of the best features of enums, right, is sort of this idea of switch statements. You avoid using magic numbers of just writing like 37 or something like this, right? Use descriptive names, and with some nice modern tooling, it will tell you if you've missed any cases in your switch, which is really, really useful for making sure that you're exhaustive matching against those. Obviously, it'd be better if it was a compiler warning, but what can you do? It's C. You know what I'm saying? You got to live with what you got. So here's an example, right, where you might say something like switch on the log level, and then you could print basically some message that different levels are enabled. It's important that you write this break after each time. Otherwise, it's going to print this and then go down to the next one and then go down to the next one. And we'll keep on executing all of those. In some cases, you might want to do this. There are real world cases where I've seen this, but usually it's just a foot gun that you accidentally forgot to put a break here. You can use it to do multiple cases in one. This is more common, where you say like, oh, I have 3 things. They all take this path. These 2 might take this path, and here's the default one. But most of the time, every case you want to have a break. That's how you should be thinking about it here. So we have now an enum of HTTP requests, right? And we might want to just, yoink all those and put them in here, right here. And, oh, I can't actually do it that way. Okay, nice. Copy, I guess. Okay, nice. And then we'll paste those in. So this, I just did this so that I can easily remember which ones each of these are. So now what we're going to do is we're going to switch off of these. So we can do switch, and then you need parentheses, and then the thing you're going to do, and then you need to do cases for each item. So you would go something like case, this, and then we're going to go like here, case, HTTP bad request. Now what are we going to do? We're going to return, and then HTTP bad request, we want 400 bad requests like this. And then we'll go case here, and we'll go to here, and then we'll say return, and 401 unauthorized. I know I'm going to mess one up. I'm going to try and nail this one first try. 404 not found. This one's real. If you don't believe me, you can just look it up, but it's real. Return 418, I am a teapot. That's a real HTTP code, okay? We're only including the best, most relevant possible knowledge for you here, okay? 500, internal server error, okay? And you can actually see, like, this looks pretty nice, right? And then at the bottom here, we can go default, and we could say unknown HTTP status code. Like this actually looks pretty good. You know what I'm saying? Like it looks pretty easy to read and to handle. I like this switch and case and handling each of these. And there we go. We got it all. Size of on enum works similarly to how you might guess it would work, which is that most of the time enums are just an int. However, sometimes we put in really big numbers that don't fit inside of the integer type that we have. So in this case, what you'll see here is we want to print the two different, we'll talk about this part first, right? So basically, always, if it can, C is going to fit it into the smallest like integer type that it can, right? So if these all fit within one int, it's just going to have it be int. If it needs to go longer, maybe it'll do like a long, right? And so that's sort of where we're at with how it generally does it. And as we talked about before, these are really just fancy integers, right? Small, medium, large, extra large. They're just ways to use a name to represent a number, because code isn't just for the computer. Code is for your coworkers and for you in the future, okay? So most of the time this doesn't matter because you usually don't have any big numbers, but occasionally this might make a difference. So what we want to do is we want to print this right here, and we want to print those like this. So let's go print F. And let's give this ourselves a new line. And then this big numbers is Y bytes. We can do ZU, and then we can go size of big numbers. And then we can do basically the same thing here, which is this %ZU bytes. And then we'll go here and size of, and we call this one HTTP error code. Right. And we did call that big numbers, right? Yep, we did. Okay. So we should submit this and get the right stuff printed out here, which is just that big numbers is 8 bytes because it's a bigger number here. If we kept going, I actually don't know how big of a number you'd need to get for it to be passed here. We can just try running this. That's too literal to be represented by any type. Nice. I don't know how big. I actually never gotten that error before. That's pretty funny. That must be because we're on the WASM thing here inside of bootdev. Like you can definitely make numbers that big when you normally do this, which that's very funny by any single integer type. Maybe this will be 32. No, it's still just 8. So it must be 8 bytes is the biggest that we can do on this WASM platform. On your computer, you could type a bigger number and you could get this to keep on going to higher sections. But anyways, I just think that's kind of funny. That's sort of interesting what's going on with size of enum there. Now that we know about structs and enums, we're going to learn kind of the last sort of like keyword style thing in C. This is about unions. And like I mentioned here, this is not like when Google employees are complaining that they're underpaid and don't have enough oat milk. This is a feature that even Golang doesn't have. Again, Lane, truly in shambles, okay? Truly in shambles. So basically, a union in C can hold one of several types. They're kind of like, if you're familiar with the term sum type in functional programming, it's basically like it can be this thing or this thing. So it can either be an age or a name. And this can either hold an int or a char star, but not both at the same time. Okay, so they're not fields. It's one of these options. Okay, one of these things is the union. Now, once again, because this is C, right? Because this is C, you're going to see some goofy stuff here. The reason for this is, let's say we set age equal to 29. Cool. Lane.age 29. Nice. But here's where it gets interesting. What happens if we try to access the name field, even though we set the age field? It still works. There's not like an error. There's nothing else happening. I mean, really, works in the loose sense like C. What we have is undefined behavior in a way, right? And so the union only reserves enough space to hold the largest type in the union. And then all the fields share that same memory region. So when we set age to 29, we write an integer representation of 29 to the lane union. And if we try to access name in that same box of memory, it's going to interpret as char star, which is why we get garbage. So simply setting the value of age overwrites and basically changes whatever you had there if you had put anything in name before. They're all sharing the same memory, okay? So for us, though, what we're going to do is, if you recall, we're talking sort of about this snake laying kind of thing that we're making where we're implementing the garbage collector for our object system. We need to build objects first. So first thing is first is we're going to go check out our snake object. It says right here, we can either have ints or strings to start with. And then we have a snake object, which is going to tell us its kind, and its data. Okay, so here's its union right here, right? And so the first thing that we need to do is we're kind of missing, right? We're kind of missing us saying what the snake object kind looks like, right? So we need to build that. So we can go typedef union snake object kind. And then we can go here and we can say this is going to be either something like integer or string. Okay, those are our two options. Oops, sorry, this should be enum. And then we're going to do this as snake object kind t. And I know these names are a little longer than what they do inside C. That's okay. We're trying to make it so it's easy to read. Okay, so that's the first thing. Now that we have that, we can go back to our exercise and we need to do something where we print out int and then the number or string and then the str. So that's actually not too bad. What are we going to do here? This pattern, you're going to see this a lot, so be paying attention. Switch obj dot kind. Okay, right? When we go back over to here, we see kind here. That's the enum we just made, right? And then we're going to say something like case, right? Case. And then we can go integer like this. And then what are we going to do? We're going to say printf. We're going to print off and we'll say int and then the number here, which is obj.data. Okay, so that gets us to our object data, but now we need to say vint. So we'll say obj.data.vint. We know that it's an integer there because, why do we know that? Because that's how we're going to construct them. Case string, we'll kind of yoink the same idea here. Now it's going to be string and %s, and then instead of being vint, it's going to be vstring, and then default, right now we don't have any way to create anything else, but it's just a good idea to have. We just say unknown, something like that. I don't know. I don't think it's going to come up because we don't know how to do it yet, but that's okay. Right, so that's how we can do this. We have our case. We're going to return because we don't want to do anything else after these, and then that's it. So this makes a new integer right here. Yep, that all looks good. That all looks good. Okay, so let's just give that a submit. And then that's how we're going to print those off. So now it says, hey, int 2014 buffer 2014 equals nothing, formats integer. Let's see what thing we failed here. Oh, I see. What I need to do is actually do sprintf, and we print this to the buffer that we're trying to write to, instead of just writing them to standard out, which doesn't do anything. So once we have this going, now what we should be able to do is submit this, and we'll get those to run. That's one of those things where it's a little bit more easy to see once you read all the directions. Like we were alluding to in part 1, the memory layout for unions is that they share the same memory location, no matter which field or types you're actually using. So if you access something that you didn't set, it's basically almost always a bad idea. We'll give you an example of where it could be okay, but generally speaking, it's a bad idea. So take a look at this val or air. In this case, we have an int value or we have some unsigned int air, okay? And run the code in its current state. So it says value set and error unset. When we do lane score of -420, the error value is some really large integer. Why is that? Well, it has to do with how negative numbers are stored in C versus unsigned. We don't have time to get into exact layout shenanigans there, but you'd probably have thought that it still would have done, -420 for both because they're both integers. No, unsigns are stored differently than signed integers. So now what we need to do is we're going to uncomment this block and then run it without submitting as well. Okay, and we'll notice how now the air field, an unsigned int, is set to uint max, which is a constant, and as expected, this prints that big number, but the value prints -1. So it's interpreting the bytes that represent this number as the unsigned integer as signed integer, which is -1. So this is basically like just going to show you that really weird stuff can happen if you try and access not the most recently set item in a union. Don't do that unless you know what you're doing. So we can submit those and then that will work just fine. It stands to reason that since all of the, we'll say, fields in a union share the same memory layout, that the largest field has to be the one that determines what the size of a particular union is, right? And so if we look at this example here, we have int data and some char air 256. Even though data is only going to be taking up 4 bytes, we have to use 256 bytes to store it every single time because we're going to use the same memory layout. So that's just something to sort of be, thinking about in your head as you make enums, is you want to try and not put necessarily too much data directly into the enum if some items are quite small, because you may end up basically creating a lot of wasted memory that doesn't get accessed. So in the following example, it's asking us how many bytes will be an instance of sensor data. Well, if long int is 8, and these are all just long ints, then we know that it's 8 here, and that's the right answer. For the next section, it's a little bit trickier. So we know that this one's 8. We know that this one's at least 256. And then we know, look down here at union, this is a struct here, a union of structs. So we have 1, 2, 3, so that's 12, or 1, 2, that's 8, or 1 here, that's 4. So this one is 12. So we know that this one's 8, we know 12, and then we know this one is at least 256. So that makes sensor data, item, and packet payload our correct answer for that. So even though before I said in general, you really don't want to access things inside of union, I'm going to show you an example of where this is like the only case I can think of where when you set one value, you can access other items. In general, not a good plan. Okay, not a good plan. The only reason that I'm showing you this, though, is because I just wanted you to see that it is possible to do and understand it, and to connect the ideas here. And so it'll become clear by the time we're done with this section, right? So if in this section we have typedef union color, we have some components RGBA and some uint32 RGBA. So these fields, 8 plus 8 plus 8 plus 8, that's 32. So these take up the exact same amount of space. And these are well-specified units in C. They always take 8 bytes, okay? Or 8 bits, sorry. So it's 1 byte here. So we have our R, and then our G, and then our B, and then our A, and it lines up in the same RGBA spot. So that's pretty cool because of how this works. Now, there are some things with endianness and some other problems you might have to run into depending on the system. We're not really going to cover that example here. I'm just trying to give you a feel for how this might happen. And yes, I agree with Lane. The fragility of C. You really shouldn't do this, generally speaking. Just do a little like arithmetic and get the right answer out anyway. So in this case, we're going to make a packet header union. It should have 2 fields. The first one should be a struct, and it should be TCP, and we can go something like, we'll just make it here, typedef struct, and we'll just call it like header, or I guess we'll call it TCP or something like this, right? And we'll say that its first 2 bytes are source port, and the next 2 bytes are the dest port, and the last 4 bytes are the sequence numbers. So for this, I would use something like uint16t, and go source port, and then I would go the next 2, so we can go uint16t dest port, and then we can do the last one here, t, and the next one is uint32t, which is which is sequence num, and this should actually be dest port like this, and that should look good. So that looks good. We should be able to go TCP header like this, and we can say TCP header, and we can just call it TCP header. Maybe we don't want to call them the same name. Oh yeah, sorry. I should call this _t because that's what we've been doing. So that looks good. And then the other one is raw, and it's just 8 bytes. And so for this, we could just go something like, I don't know. We could just say char 8, maybe raw, something like this idea, right? So let's give her char like this. Sorry, we could go like this, char, and then 8, so that we can just put the same values here. I don't know if that's actually what we're expecting here for raw. Let's see what we use. Do we use raw here? Yeah, and that looks pretty good. Or we could just do this as uint8s. That's probably fine too. uint8t is also good. So let's give that a run and see if that compiles and everything's happy here, right? Because it should be 8, 16. 32, 64, 8 times. Yep, now that looks good. Let's give it a submit and see what happens. And so this does exactly the same thing as sort of this idea here, where we're specifying 2, 2, 4, and this is just, 8. So those work nicely. They overlap perfectly, and we make this same picture here. All right, and now we are getting into chapter 6, which is the stack and the heap. First, we have to cover the stack, which is the simpler of the two. When we're talking about the memory that we have, right, we do really think of it as a giant array of bytes. The address is at different values, right? But we do some additional structure to what's going on. Obviously, we don't just think about it as one big array. We do a few other things. And so the two main regions we need to think about, at least for C, are the stack and the heap. And like I said, we'll cover the heap later in this chapter. Whenever we create a new whenever we call a function, we create a new stack frame. There's some other ways, blah, blah, blah. But like this is the main way that we're going to create a stack frame. And what this does is it gives us memory to store the local function's parameters and its local values. And when the function returns, we deallocate that entire stack frame. And it's this sort of last in, first out, right? Because if you're thinking about like calling functions, if a function calls another function, right, as we sort of go down into those, we don't want to free any of the stuff that's from this top function, right? We only want to free them, the most recent one that we've done. So we show an example here of create typist, right, which has int whether they use neovim, right? We don't use this in the function. It's just an example of where these would get allocated. We have a local integer, and then we have, an array or a string of characters. And so when we call something like create typist1, the first thing that we're going to do is we move the stack pointer and we make room for whatever type we're going to return. In this case, none, so that's not so bad. The arguments to the function and the local variables to the function body. Right, and so we have a return address and the stack pointer. Then inside of here, we see this uses envim, right? That's from this argument here. And then we have our words per minute. That's our local integer right here. And then we have our array of TEEJ, right? For a character array of this, and then there's a null character not shown here. So when this function returns, the stack frame is deallocated, right, by resetting the stack pointer. So you can think about it just kind of goes back in time to these, and then we might write over this later. So the way that we have it right now for this assignment is it says run the code like this, and then we're going to see that each of these locations uses a different pointer offset, right? We're setting a different memory location here. And so if we instead change these, right, because what it says, we want print message 2 and print message 3 to use the same stack space. So the easiest way for us to do that is we need to call these sequentially now from the same sort of parent function, so that whenever we enter inside of these functions, we are first creating the stack frame and then releasing it, right? So it's like create, release, like this. And so that should give us our submit, and that should work just fine. Nice. Let's head to the next lesson. So why a stack? We alluded to this a little bit in the previous lesson, but the reason here, right, is we're thinking about this is the faster and simpler version. We always know that we're going to sort of linearly grow and shrink the stack frame instead of randomly adding stuff. And so this lets us do efficient pointer management, right? And an allocation is just changing where an address is, which is really good. It's cache friendly in the sense that when we're loading these variables up, we're probably going to access other variables that are close to each other. And so that's going to make our computer go zoom, zoom. The stack is automatically managed for us, right? We never have to call anything like free on a local integer. C handles that for us. And there's, some nice things about thread safety because of stack frames being isolated and all of this stuff. And Lane's going to say something about Go, but I don't care. So anyways, what are we going to do? Is it more performant to store a variable's data on video cassette, tape, stack, or heap? So it's stack, because that's the fast one we just said. So right here. Let's go to the next lesson. So one of the problems that we can have with the stack is that it is possible to overflow it. And this is indeed where the site Stack Overflow got its name. And I'm kind of thinking, is Stack Overflow even relevant enough to mention anymore? I don't know, but that's fine. It's where ChatGPT mined all of its information from. So that's sort of one thing to note, is that it is possible, especially in language without tail call optimization, like OCaml, it's got that. You can possibly, if you're like recursively calling functions, you can exceed the amount of stack space that you have. But generally, this is not so much of a problem. In this example here, snakelaying is a fairly inefficient language. Actually, I think we should tell the VC investors. From what I've seen, that's what they prefer. And so what we're saying here is we actually don't want to allow basically 1024, and times 10. We only want a single Kippy byte. So if we delete this here, and now we let ourselves run this and submit it, we're going to make sure that we don't accidentally create something that's so big that we can't fit it into our stack anymore. So that prevents a stack overflow for us in this case. So as we mentioned, when we think about the stack, the important thing to remember is that it's just this big continuous area of memory that we're sort of changing where the stack pointer goes. And when we release the stack frame, we move that back, which means any data now could be inside of that region of memory that we had before after we clear or exit the function that we called. So here's an example of something that could go wrong. We're back in our 2D graphics library. We've got a coordinate. It's got X and Y. And in this case, we're going to return a pointer to a new coordinate. But the problem is we create this pointer right here in the stack frame that's going to get freed when we're done. So let's run this and see what happens here. You'd expect to see, 10, 20, 10, 30, 40, 50, 60, right? Because each of these are sort of like new pointers. But instead, we get 50, 60, 50, 60. Now, in this case, you're sort of lucky because all of these are going to line up because we're not doing anything complicated in here. Normally, something much worse happens because you're calling like 37 different functions in between where this happens. But in this case, we kind of get lucky because this coordinate C is the same location in memory each time. So we accidentally return the address to the same spot for each of these functions. So what we need to do instead is we need to just return a new coordinate like this, and then change each of these to just print the actual the actual fields themselves instead of being inside of a pointer. And so that should do what we want now because we're going to create new memory each time and return those separately instead of pointing to the same spot in an invalid stack frame.
The stack and the heap aren't just abstract concepts that are applicable when writing low-level C code. In fact, they are useful even if you're having a bad day and being forced to write TypeScript. The stack and the heap are two different regions of memory. The stack is simpler and faster, but it is a bit more limited. And the heap is slower and a bit more complex to work with, particularly in languages where we manage our own memory, but it does allow us to create more sophisticated and complicated data structures. Let's first start with talking about the stack. An important thing to remember as we work through this in C is that C always needs to know how large some piece of data is and where to put that data. So when we look at a function like this, for example, create typist, we have some input variables, which we usually call arguments. For example, uses envim. We also have the words per minute and a character array for a name. C needs to know where to put all of these so that it can access them later. Remember, everything in C is about having some sort of name, an address, and then a value. The C compiler knows how large each of the different data types are, and it does not need to dynamically allocate any of them. So they'll all be placed onto the stack. And in this case, and roughly in C, you can think about getting a new stack frame every time you call a function. So when we call create typist, we're going to create a new stack frame. This means we're going to have a return address and the new stack pointer. The return address tells us where we're going to go once we're done with this function. So after everything's completed executed, we'll move the stack pointer back to this spot in memory. The stack pointer tells C where we currently are in case we have another function call and we need to create a new stack frame. The first thing that's going to be put into the stack frame are any arguments to the function. In this case, we just have one argument, uses envim, and so that will be copied into this stack frame. Very important when we're thinking about function arguments to remember that they're getting copied. The second thing that's going to be put into the stack frame is the int that is inside of that function scope, which is words per minute. And then lastly, we have to reserve space for each of the characters of the array, and so we have the TEEJ characters stored in that stack. Once this function returns, then we will move the stack pointer back to the return address, effectively freeing all of that memory to be used again later if we have another function call. Now compare this with the heap. Instead of being this static array of memory that we sort of push and pop off the top of, the heap is much slower because we need to dynamically allocate this memory and grab new resources from the operating system, as well as a bit more complex because it is possible to forget to free that memory, at least in languages like C, which would lead us to memory leaks and possibly running out of memory completely on the computer. So you're probably wondering, why would we ever want to use the heap? It's slower, more complicated, and can lead to memory leaks. We are going to use the heap because sometimes we don't know the size ahead of time of the different objects that we're going to use. Now, consider the scenario where you have a list of users. For a lot of you, you may know ahead of time that that list will always be empty. But for some cool people like Lane, I will admit he does have a few users. They may have to dynamically allocate something like all of the users who haven't logged in the last 3 months. Because we don't know that number ahead of time, we may need to dynamically allocate and continue to expand a region to store those users' data as we get more and more users to put in the list. So generally speaking, what you should be thinking is the stack is for things that we can know ahead of time and that only need to exist within one function. And the heap are for things either that we don't know the size ahead of time or that we need to return back outside of the function that may have some allocations.
Wow, what a great video. Anyways, let's talk a little bit more about the heap. The heap, as opposed to the stack, right, is an idea that we're going to be using to manage things that live longer than the function that creates them, right? So this is how we can share data between different functions that create them. We can make things that we don't know the size ahead of time for. There's a lot of reasons why we want to use the heap and why we sort of have to use the heap. And so when we need to store data that outlives the function, right, we're going to put it in the heap. Or if we don't know the size ahead of time, there's a few other reasons why you might use it in C. And so in this case, this is an example of creating a new int array. And this says, hey, I'm going to return a pointer to, there's an int array, and you just tell me the size that you want. What are we going to do here? We're going to create a new array. We're going to use malloc, which is memory allocate, and it's going to say, hey, make it the size times whatever the size of integers are, right? So if this was a wide integer, maybe they could take 64 bytes, or maybe they could take 3 bytes, or maybe there's, you could have a whole bunch of different sizes. In this case, it's just the size of an int, so that's not so complicated. But we need to make sure we allocate a big block of memory contiguously of that size. You check to make sure you don't accidentally have null, because that can be bad. And then we return the new array here. And so basically what this does is this creates this little array here in memory, and malloc is going to return to us that location, which is what we store before. And so now once we have that and we get this array returned to us, we can actually set the values just like you might for any other array. And this is actually stored on the heap, which is good because when we return from this function, the stack frame does get deleted, right? Or it gets cleared, it gets pushed back the way that we're talking about it before. So we need it to be living somewhere else. Otherwise, we'd be accessing invalid memory, which would be really bad. But to make sure that when we're done with this, we need to tell the operating system, hey, I don't need this array anymore. You gave me these, 6 bytes. I don't need those 6 bytes anymore. I want you to have it back. And you need to tell the operating system, hey, I'm all done with this. It's free now. And so you tell the operating system that with free. And that deallocates the memory so that the operating system can do something else with it. There's a bunch of other things that might happen, but generally speaking, that's how you should be thinking about it. I'm all done with this. You can have this back, operating system. So right now we can run this function and we'll see, hey, we're going to be calling get full greeting in main.c. We try and make sure here that we're going to say get full greeting, hello Alice 20. We want to assert that these things match, but they do not. Why don't they match? That's because right here, we're using the stack memory that we had before. So what we need to do now is to make sure that this isn't allocated actually on the stack, and we can do that with malloc. We're going to make sure that we get it the size and then the size of char. This is a good pattern to do even if you don't need to do it for char. And then the trick here that you need to remember is to make sure that we only try and copy in the right amount of size here. so that we don't accidentally paste in past the size of our buffer, because that would be really bad. Now, when we hit submit on this, we should get everything works just fine, and we'll head over to the next lesson. So in the previous lesson, we used malloc, which is the memory allocation function, and it's a standard library function in C that you should get used to if you're going to do manual memory management. And it returns the number of specified bytes that you ask for in a contiguous array, and then returns the pointer for where that array is. One thing to note, and it's very important, is that this new memory is uninitialized. So that just means there's no guarantees what is in there right now. So if you want to make sure that it's all cleared, you can use calloc to do so. After you're done using it, it is your responsibility, you, the programmer, to make sure that you use free, otherwise you will memory leak. And it looks like this. It returns some pointer, it takes a size, and that's it. So what are we going to do? Here's the example that we kind of just went through, right? Is this idea of mallocing, and we're going to use it, and eventually we free. And so this is, like we say here, the manual in manually managing memory. This is not like garbage collection, right? The garbage collector is the one that decides when things need to get freed for you, which we'll talk about later in this course. But for you in C, you're the one that has to remember to do so. And in this case, you'll actually see right here, we do call free at the end of each of these examples just to make sure that we call them correctly. So that's great. So now we want to do is we want to create something here that makes a scalar list. And basically, it's just each element should be whatever index times multiplier is. So let's make ourselves something like int star result, and let's malloc ourselves something that's size times size of int here. And then for each of the locations in this array, we need to set it to this value. So we can check here if result equals null, right? Then we're going to return null like this. Otherwise, we're going to do for int I equals 0, I less than size, I plus plus. And then we're going to set this to result I is I times multiplier, right? Because that's how we're going to make sure we get in each spot. And then we can return the result like this. And I believe we remembered everything here that we need to do. Int size, right, like this. Yep. And then we should be able to run this just fine. And if we submit this, that'll work. And like we said here, in this case, the malloc is happening on our side and the freeing is happening from a caller, which unfortunately usually has to happen in some ways, right? Because this is the problem with the managing the memory, is there is just going to need to be an understanding or a loose contract between you and the other people writing this C code that we're going to free at particular times. And we're going to go over that more as we go a little further. And now that we've practiced allocating the memory, let's practice freeing it. As we said before, free is sort of the counterpart to all of these allocation functions. It is important to note, free doesn't change the pointer or the value itself or anything like that. Instead, it only alerts the operating system, I'm all done with this memory, and afterwards, you do not want to use it. You will have a bad time. That's called use after free, and it is not good. The primary problem for forgetting to free is you're going to just keep using more and more memory forever. You will never give it back to the system. Maybe for some of you, if you only have one user, your app might be able to survive for a little while, but you don't want to sort of rely on only having one user forever. So in this case, when we run this code here, it's going to keep on creating all of these lists. But the problem here is that it says, hey, eventually we've run out of memory. I can't keep allocating these ridiculously large lists. So what do we need to do? We need to make sure that we free this list every time we're done with it, right? We're not using this list anymore. And so now when we submit this, we're going to allocate it, do a little thing with it, and then free it, and then we're all done. And while we're talking about how these things are stored in memory in these arrays, one thing that is at least of useful info for you to have heard before, at the very least, is this concept of big endianness and little endianness, which is such a funny word. I don't think it's named after anything. I think it's just literally because which one is the end. And so programmers, of course, were like, well, let's just call it endian. Don't quote me on that. I'm sure we're going to see that in the comments later. TJ says endian. Whatever. I don't care. Leave a comment if you want. But anyways, in big endian systems, the idea here is that the most significant byte is stored first. Okay, so when we have 1, 2, 3, 4, 5, 6, 7, 8, right? A quite large hexadecimal number. You see here, you get 1, 2, 3, 4, 5, 6, 7, 8 in each of the bytes. Okay, so that's the biggest part of the number goes in the lower address to here. Now, there was a whole big culture war about this between different people making this. It doesn't really matter. Okay, you just need to know that these things exist. And in little endian systems, the least significant byte, right? So we see 1, 2, 3, 4, 5, 6, 7, 8. The 78 goes down here. The 5, 6, 3, 4, and 1, 2 go here. And so that's how it would be stored in little endianness. So you usually don't need to handle this. C knows how to read this based on the architecture that it's in and all that kind of stuff. The main complication is occasionally when doing network or binary files, you might have to worry about this. And as we mentioned here, building e-commerce shops for the terminal instead is a much more useful use of our time. So when it asks us in a little endian system, how would the hexadecimal number A1, B2, C3, D4 be stored? So we look back here, little endian, we think about 1, 2, that one goes all the way over here, right? So we should be seeing A1 to the right, and that's only here. So that looks like it should be correct. All right, let's go to the next lesson. All right, on to chapter 7, and now we've got pointers as this great video, and wow, what a thumbnail. We're now going to get into some more advanced topics for pointers. The first thing that we're going to cover is pointers. Now, at first, this seems very complicated. It seems like it's going to be a big hurdle. But when we remember that pointers are just a value that is an address, right? Just like 1, 2, 3, 4 Sesame Street, that's a value, but we know that it actually is pointing to some other location. A pointer just happens to be an address that points to another address. In the following example, we set up two values, v1 and v2. And just like we've been doing, we're going to set up a name, address, and value for each of them to help us mentally work through what's going on. The first thing is that we have v1, and we set that at some address like 4. Okay, it's sort of our beginning address. You wouldn't want to say 0 because that would be null. So it's some address like 4. Obviously, it's going to be a big address later. We'll set that value to 1 so that we can remember v1 for value 1 is that. Do the same thing for v2. Now we're going to get to our first value. That value is checkpoint. And this is what we're going to use along the way to sort of check in to see, after we evaluate certain expressions, what values we get. So first we're going to create a pointer that points to v1. And so of course we're going to set that as the value 0x04, right? Because that's pointing to that address, right? So that's pointer just pointing to v1. Now, if we make a pointer, that is going to be pointing to, or sort of referencing, our original pointer. This is not as tricky as you might think. We're just saying this points to the address of pointer. Okay, so there's no extra magic with this additional layer. We're just pointing back to that original thing. So now we have to ask ourselves, okay, when we double dereference pointer, what is the value going to be? We can use the same tricks that we've been doing before, where we trace through our addresses and eventually get back to 1. When we get 1 here, because we're going to say, aha, we've got a pointer, we go to pointer, we dereference pointer, get back to 1. But what happens when we change pointer to now point to v2, right? So its new value that's stored in memory is going to be 0x08. Right? We're changing what the value of pointer is. And so now when we trace through and we sort of do our analysis, right? We're starting down here at pointer. And what we're going to do is we're referencing, we're going to trace through, and we see now that this points to whatever is in v2, which is going to be 2. So what you can see is that pointers, you should really conceptualize them, at least when we're starting, as just something that points to an address. And all of the same tricks and ideas that we were using before to think about how do we dereference and work with pointers, they're going to do the exact same thing with pointers. Thanks, Lane. Really captured my excellent teaching style on that one. I appreciate it. We're going to start working on some pointers. And you might be thinking, this is going to be so crazy, it can be so much more complicated. Wrong. No, we're going to make sure that it makes sense, okay? And the idea here is we just have to keep remembering about how a memory is just a bunch of data that we can address, and pointers are just values that are addresses, right? And so a pointer is just a pointer to another pointer, right? A pointer whose value points to the address of another address, okay? And when I say it out loud, it sounds worse, but I promise when we write some code, it's not going to be so bad, okay? And the way that we can move between them is we can just dereference them to get to the right spots. All right, let's work through this example, and I think it'll make quite a bit of sense. So we're going to complete this allocate int function. It accepts a pointer, right, and a raw value. Change the value of pointer's address to point to the new memory that has the value of the int. So what do we need to do first? Allocate memory for a single integer on the heap and save its address into a new pointer. So let's go int star new pointer is malloc. And what are we going to do? We're going to int just the size of one int. Then we're going to say new pointer equals is the value, right? Because now we're setting that value. We're setting something that's actually here to be that item. And then now what do we need to do? Update the memory address of pointer. So we want to go star pointer is equal to new pointer. This is so that we're saying, hey, go back one spot, get the reference to this, and set that original pointer's value to this new pointer that we have allocated. This is very important. This would not be good if we said int new value is value, something like this, or we said just new pointer is the reference of value. That's not good because that's going to be in stack memory, right? So we need to make sure instead that we're allocating this. And you just get a little hint here too, because you see a free there once we're done with the lessons. Set the raw value here. Okay, fine. We can do it this way because that's the way that the lessons have it set up. Okay, and so now when we submit this, we should see that we get each of the items. And let's just take a little bit of a gander here at this test does not overwrite, which checks to make sure that we do not change the initial value, right? We don't change it because we've allocated new memory, and that's what we're modifying. All right, let's get to the next lesson. The other common case that we sort of see this idea of pointers is that we have an array of pointers, right? So in this case, we have this int array here, and this is going to have, 1, 2, 3, right? This is our normal pointer. But what if we wanted to have a list of strings? Well, then we need a char star star, right? We need a pointer to a pointer, right? Because each of the items inside of that array are also pointers. So that's the only way that we'd be able to store something that looks like this, where we are pointing to where these strings are. And so in this exercise, snakelang being a very super robust language needs to represent tokens. And this is a common thing actually if you write your own programming language, which are strings of text that represent different snakelang syntaxes, things like if, else, def, etc. And they're represented as structs. We can see them here. They've got some literal, a line, and a column. Right? And so what do we want to do? We're basically going to create something that copies a list of tokens into our own list of items here. And so what do we need to do here? We're creating something that's going to point to the address of each of these things. And so the first thing we do is this looks good. We're going to create an array that's the right size. But then here's the problem, right? We need to allocate new space for each token and store the address of the new space in the array. So let's go ahead and do that. So we can say token pointer, and let's say that is equal to malloc, and we're going to size of token t, right? So that we make sure we have enough space for it. Then we're going to set token pointers equal to this pointer. We already wrote the left half of that. And then we need to make sure that we copy the members of the input struct into the newly allocated ones, which means we have to do something like this. Pointer equals tokens I, like this, right? To make sure that we're going to dereference those. And if this compiles, and assuming I put the semicolons in the right place everywhere, okay, that looks good. We can give this a submit, and we should see that that's working just fine, right? So what do we do? First, we create a new token pointer. We set that as the value that we're going to do, and then we update this. You could also write this as token pointers I, like this. That should work too, because now we're going to say let's update the value that's inside of here. Let's copy those values inside of token pointers I, right? So those are kind of like the same thing because we set those equal to each other. So it makes sense that that works. All right. So now we are on to void pointers. And we've already talked a little bit about void before, which you can kind of sort of think of as saying nothing in these contexts, right? When we say void as the return type, it just means nothing is returned. And if we put void in like the function arguments here, it means it takes no arguments. But as C likes to do, it takes one word that means one thing in one context, and then we're going to use it to mean a completely different thing in another context. Okay, so now we're going to have void star, which are void pointers, right? And this tells the compiler, hey, we've got some like generic data here, and we want to use it to eventually come back out of that generic data. Now, when you use a void star, the compiler literally throws away all the type information that it knew about that pointer before. So it doesn't matter if you originally stored an int or a character or what, it doesn't really care at all. It's just saying, I'm going to trust you, the program author, to remember how to do this, okay? And remember what you want to convert it to. We do this oftentimes because we want to sort of have one spot where we have a pointer, and that pointer can contain multiple different kinds of data. All right. In this case, what we're doing here is we're going to say, hey, we can, instead of just doing this right here, a void star pointer is not like any type. Okay, right? It's not that you can use it anywhere you can, right? So that's the first thing for storing this generic data is you're not allowed to just use it to then say, hey, okay, I'm going to use it like it's any, like in TypeScript maybe you're familiar with. No, instead it only fits in void star, but what it lets you do is recast the pointer into anything you want it to be, right? So in this case, we cast this to int star, and then we dereference it. That's how we get back to a number. Now, if you had put something that wasn't a number here, this would still work because it's C, right? It says, I trusted you. You told me that it was a void star and then you dereferenced it to something else. That's okay. So this is where you have to be careful, but it's also what lets us hold different kinds of types inside of something. So in this case, you'll see right in this example here where we have the data types, right? Now that we've sort of gone over the syntax. In this case, we have an enum and it tells us whether we have an int or a float. And in this case, we have print value. And we can use these enums to sort of tell us how we want to print this item. Notice that for the int branch, we do int star, and for the float branch, we do float star. This is where I'm saying, like, void star pointers are really you telling the compiler, trust me, I'll remember what to do. There's nothing preventing you from casting this spot right here to float star and then trying to print it. That would work. It just wouldn't do what you wanted, right? So in snakelang, sort of, we're building up this idea that we have different objects, right? And so we have like an integer, a float, and a bool, right? And so we want to do a snake zero out function here, which is, okay, we've got some void pointer and we have some kind, okay, right? And so what do we want to do? We can do basically the same idea that we had here, right? So we can say if kind equals, and then let's see what our kinds are. Okay, we have integer. So we say if kind is integer, then what are we going to do? Okay, well now we're going to cast the void star pointer, just like we were doing before here, into a snake int t, right? So we could say something like star, or maybe we'll write it out as like multiple lines. So let's go something like this. We have snake int t obj is, and we'll dereference and also cast this pointer to this. So now we have an object like this, right? And we're going to say, hey, what I actually have here is a snake int star, which you can see that we're doing here in this example. Now I have an object and we've copied that into that same memory, right? We've dereferenced to the original location. And so now, instead of doing this way, maybe it's a little bit easier to see if we do this. Now we can go obj value equals 0, right? So now we're going to zero out this value where this thing was pointing to. And now we can do the same thing, else if kind equals, and let's see what we had here, float, right? Float. Okay, we're going to do the same thing. Snake float t obj is snake float t star pointer. And then we're going to say obj value is 0.0, right? Else if kind equals bool, right? Bool, then we're going to go snake bool. Did we call bool or boolean? Snake bool t, yep. Snake bool t star obj is snake bool t star pointer, right? You're sort of getting the idea here. Obj value is 0.
like this, right? That's false, right? And then you could also optionally have like else do some stuff here, but we're not going to worry about that right now. We'll handle that kind of scenario later. So let's give this a run and see if we typed everything correctly here. And it does give us the things here. So let's go ahead and hit submit, and we should get all of those correct now. So you can sort of see how we're keeping track of the type information sort of like almost at runtime, and then we're deciding what we're going to do with that type information. So that's a simple example of how we can use void star. All right, before we get to the complicated advanced pointers option that we're going to explore here, we're going to do an intermediate solve here. And what we're going to do here is we want to write a function that lets us swap integers. We'll do the sort of generic case in a moment, right? And so when we're doing this, what we really want to say is we want to switch, cool person and uncool person. Actually, that's true, right? I forgot I wrote this. Cool person is TJ and uncool person is Lane. Right, that actually makes sense. I was like, this doesn't make sense, but it makes sense by the end. Right, so we want to switch these two values. So how are we going to do this, right? If we only had 2 slots, that actually doesn't make sense, right? We actually need to create a third, like, temporary holding spot to say, hey, like, can you hold this data for me for a little bit while I juggle these so that I can like set this down, I can put this object into my new hand, and then I can grab the other one from here. So for integers, this is kind of easy. We can say int temp, and we could do something like get the value from A. Now we say B is A and A is, we'll go A is B, and we want to say B is temp. Okay, right? So we're going to copy the value from B into A, then we're going to put the value from temp back into B. And if we run this, we should see that's kind of like the juggle, right? We set A down, okay, and then we grab A, put it in this hand, and we reach over here and grab B to put back for temp. So we submit that. So that's the simpler version, and then we're going to do the more complicated version coming up right now. Okay, so now that we've done that for integers, we're going to take the same sort of idea here and do this again for swapping strings. The tricky thing here is just getting past reading double star and sort of don't freak out about that, but just remember what we're trying to do here. We need to do the same dance that we just did, right? Where we only have 2 hands, so we got to put one thing down, then we can grab this one here, and then we can grab the other one, right? So we can do something like char star temp, and we can dereference A. And now we could say B is A, and I literally did the same thing again. A is B, B is temp. Just temp here. All right, so what are we doing? We're going to set A down, and we're going to put it here. Now this is a little bit tricky because you're thinking there's still a star on this side, right? But that's because this is 2 pointers deep. We're going to dereference to make it 1 pointer deep, right? So we're going to save that address, then we're going to swap the addresses, and then we keep going. Okay, so that's what we're doing here. So it's really similar idea to what we had before, right? Where we're going to keep that value, but this time the value, instead of being the integer itself, is actually a pointer or an address that we want to store. We're going to want to remember this as we get to the next section. So in the previous 2 examples of swap, the trick was we already knew what the size of the data was going to be ahead of time. That's how we could just say something like int temp, or we could say char star temp. We already knew what the size of those data types were. But here's the problem. If we want to write a generic one, we can't just statically allocate the size of that thing ahead of time. We can't do that. Instead, you should hear, we can't do it statically. You should be immediately thinking dynamically, we're going to have to allocate some memory, and then remember to free, right? So we're going to use this memcopy function to do a little bit of that as well, right? That's going to actually copy the memory from one spot to another, but we're also going to need to remember to make that like temporary spot that holds the variable that we need, right? So how are we going to do that? The first one, we'll do something like void star temp, right? And now we're going to malloc the size, right? So now we're going to get the size back of this. And you're saying, sweet, okay, that's good. So if temp is null, then we're in big problems. So we'll just return here. Okay, we'll just return. What are we going to do now? Now we need to say mem copy. We need to copy from our void pointer 2 and put it into void pointer 1. But we actually can't do that yet because we need to put what's in void pointer 1 into the temp.
right? So this is where things are a little bit different. So we go mem copy, and we're going to go destination, that's temp. We're going to take our first thing here and size, and we'll copy those in. This is really similar to where we said, like temp equals A, okay, right? Now we want to go B equals A, right? This kind of idea. We're going to go mem copy, VP2, VP1 size, right? And now we're going to go, oh my goodness, I did it wrong. I'm going to do it wrong 3 times in a row. It's incredible. No, this is right. We're going to copy VP. We want to copy VP2 into VP1. That's what we want to do, right? And now we're going to say, because this is the destination, so we want to go A is equal to B. Now we need to go B is equal to temp, right? So we mem copy into VP2 from temp the size. Wow. I can't believe that I did that wrong so many times in a row. And here's the trick, as we helpfully mentioned in the assignment, we have to remember to actually free temp. Otherwise, this would leak, right? So when we create the holding spot, we actually need to we need to get some memory, so that we can copy things into it, right? We're going to copy from the source into the destination, right? So it's VP1 into temp. Then we need to copy 2 into 1, and then we need to copy temp into here. And then now we're all done, so we can say this. So let's test running that out and see how that works, which it looks good. And what you'll see over here, what's cool now is like this works for ints, right? We can pass the addresses of ints, but it also can work for like different strings, right? It can work for strings, and it can even work for mentioning terminal.shop, the excellent coffee shop from your terminal, by the way, right? And so we can swap these around, even though these are all different data types. We do that through the use of void pointers, right? We can basically make a function that just operates on a slice of memory, and we can give it different slices of memory. Now, the tricky thing here to remember too is like there's nothing preventing you from doing something bad where you like put a pointer of a different type here and try and copy them. C will just let you do that. That's what happens once you start playing with void stars. So that's everything we've got going on there for void star pointers and advanced pointers. Let's go ahead and get to the next chapter. All right, now we're on chapter 8, stack data structures. If you don't know what a stack data structure is, we'll do some brief, explanations and reminders, but we've covered this earlier in some boot courses. So if you need to, you may want to go check that out, or go check out just reading. Like, it's a pretty common data structure. You can just go like to here in Wikipedia and read this. So what are we going to do? We're going to actually apply some of what we've learned about these void star pointers and generics and allocating memory. We're going to start making some data structures in C, and we're going to build some functions that are associated with that. So we're going to build a bunch of the functions here from snake stack H, right? Because it's sort of like for our snake thing. And we're going to have a few different options. We've got, the count, which is how many items are inside, right? And the number of elements. We have a capacity, which tells us, hey, how many things can we fit inside of here before we need to resize it? And then we have this void star star, which is saying, hey, we have an array of void star pointers. Okay, this is where we're going to keep all of our data. The reason that we have to do this with void star is because otherwise we can't store like things of different length in the same spot, right? If we had a struct that we wanted to store in our stack and it was, 64 bytes long, we can't put something that's only 8 bytes long in the same kind of data structure. We actually need to point somewhere else in memory so that we can keep those evenly spaced. This will become more clear as we get a little further in here, but that's just sort of the inspiration why this must be void star, right? It has to be an array of void star pointers, right? That's how we get generics, right? So what are we going to do? We need to first implement a stack new. This is kind of like the easiest one, right? So the first thing we need to do is we need to return a stack. It wants us to return a pointer to a new stack. So first thing we need to do is we need to say stack T, we can call it S, right? And we need to malloc something from the size of a stack T, right? So now we have a new stack. Awesome. We once again check here if this is null. Okay, we need to return null as well here before we access it, because that's bad. Great. Now we need to do something here. We need to initialize to our default values. Count, right, is 0. Okay, we're not storing anything inside of here. Now we need to say S capacity. We need to set that to the capacity that we said, right? That's sort of, we're initializing to a particular capacity. Maybe you're going to put at least 64 items in here. Okay, well then initialize it to 64 so you don't have so much back and forth with the operating system resizing things, right? All right, then what are we going to do? We're going to initialize the data, right? So this is like S data. What are we going to do here? We need to malloc enough new memory that we can fit all the void star pointers that we need to. So we can malloc here and we can say size of void star, right, times capacity. That's going to make it so that we have enough space to put all of these pointers here in data, right? And then if S data, is null, then we're also going to return null here, okay? And otherwise, we can return S. So that's awesome. So this should let us do something where we initialize something to stack 3. We're going to make sure that we get a capacity 3, there's no count, and that it's not data. Then we'll, of course, need to free everything in the tests, and then make sure that we didn't allocate anything that we shouldn't have. And so assuming that we typed everything right here, we get an okay on that, so we can give it a submit. And that's basically the first step, right? So now we've made an empty stack of the particular size that we need. Capacity is probably a better word to say there. And now we're going to start implementing other functions for this data structure. The first function that we need to do is push. This is the one that's important, right? We're not just going to just allocate this for no reason. We need to actually store some data for a practical purpose, like not like Haskell, right? This is C. We need to ship something like a library, I guess. Maybe you wouldn't want to use C to ship your SAS, whatever, but you know what I'm saying. So as you know, our stack has count and capacity, right? But what happens when count is equal to capacity? That's where we're going to have problems, right? Is we need to make sure that we allocate a larger amount of stuff. And the normal, like a pretty common approach for this is whenever you run out of capacity, you just double the size. So that way you don't have to have this thing where you're constantly reallocating and doing all this other stuff. That's not good. We don't want to have that. Instead, what we want to say is like only occasionally we're going to have to do the really expensive thing of asking the operating system for new memory. And then we'll just work with that block of memory the rest of the time. So how are we going to do that? We need to write this function that's going to check the capacity and make sure we have enough space to do this. And if we do have enough space, then we will just push the item on here. We'll set it in there. Otherwise, we'll allocate more memory. So let's do that here, right? So this is step number 1. We need to check if the count is equal to the capacity. So if stack count equals stack capacity, right? What are we going to do now? We need to do something like this. We're going to say stack capacity times equals 2. So we're going to multiply the capacity by 2. Now we need to reallocate the memory. So that's actually going to use realloc. And in the tip here, it gives you a little info, which is that realloc is basically like, hey, operating system, I've got this block of memory. I want all of the same things that are inside of it, but also some more. Okay, or I guess less. I actually don't remember what happens if you go less, but usually you only use this to do it for more, I feel like. So now we need to do something like this, which is stack data. We're going to get potentially a new pointer, right? Realloc could potentially use the same slot, but it also could give you a new pointer, right? So it could say, okay, you wanted, instead of 100 KB, you need 200 KB. Oh, well, I actually don't have any space where you are right now. So I'm going to give you a new pointer. I'm going to put you in a new address so you can have a bigger house, right? To put all of this data. So we're going to do something like this, realloc, and this is going to take stack data, and now we need to give it a new size. So we can say size of void star times stack capacity, right? So that's going to be the new size that we're giving here. And that reallocs this to something bigger, right? Because now we've doubled this. And so if this fails, it'll return this. So we need to check if stack data is null. Okay, then we're going to just return. We can't do anything about this. It's kind of like it's game over here, right? But if it succeeds, then we're going to say stack data, and we'll go stack count equals obt, right? We're going to put the object inside of there, and then we need to make sure that we add 1 to the count. Now you could do this in one line. There's, okay, sure. We can show some examples of that later maybe, but I want to write this at least for now for us to think about this. But here's the nice thing. This is actually going to be the same thing that we do down here, so we can move this here because no matter what, we want to put the object in the last spot in the data here, and then we're going to increment the count so that the next spot, right, we're kind of like keeping a pointer here along the way of where in the data that we're going. So we add this to here, to the count element, and then we increment the count. So if we run this, That should work, assuming we typed everything correctly again. And yeah, that's looking good. And so just as a reminder, basically we're saying, oh, do we have enough? Are we at our limit? If we are, give me more space. And then we always just put an item here at the end. So that's stack push. So now the thing that we need to do is we don't only want to push things into the stack. We also need to like remove them later, right? So the pop is actually pretty easy, right? Because in the pop, we always have enough space to return something. We don't need to do any new allocation. And so in this one, we can just do something like this. If stack count is 0, okay, what are we going to do? We're going to return null. That's sort of saying, hey, we didn't have anything left. Otherwise, we're going to do this. Stack count minus minus. And we're going to return the last element in the array. So I would do that something like this. Return stack data, stack count plus 1 here, right? Because we need to, no, we don't actually want to do that. We want to say the count is for where the next item is going to go, right? If you think about push, we put it in this spot. So we need to pop that back here. Right, because now we're sort of saying, if you think about this as like a list, right? If we had 0, 1, 2, 3, right? We're going to move ourselves back from there and give you the last item. So that should be just fine here. And it also makes sure that if we have no items in here, we're going to do nothing, right? So that's what we want to do there. So that should, it doesn't actually, in a sense, remove anything. We didn't put anything there in its place, but we don't need to do that. We just need to keep track of where the index is that we're going to. And now, of course, in a course about memory management, we need to remember, hey, we need to be able to clean up this stack. It's nice if you make a data structure to give some function that can clean up the data structure in case for any reason you change some of the underlying methods or there's something it's very easy to forget. Because in this one for stack, it's easy to remember to go free stack. Kind of easy. It's still pretty easy to forget this. But we have a problem. We need to make sure that we remember to free the data too. So we need to do something like this. If stack is null, right? We're not going to do anything. We're not going to try and free that. So we'll just return here. Okay, right? And then now we need to check if stack data not equal to null, right? Then what are we going to do now? We're going to say free stack data, right? Or you could just write maybe like if stack data. Both of those would kind of work, but we'll leave it like this for now for it to be easy. And then we need to remember that we're going to free here. So this is kind of like the tricky bit, easy to forget. Whoops, forget. Right, so that's why we write a function like this to help us remember to do that, so that anywhere else we can just call stack free. And in our case, we're going to assume that anyone who calls stack free has already freed any of the like items that the void star thing points to, if necessary. So we can check this here. And that should work. Yep. And then we can submit. And so that works just fine. We're happy with how that's working. We now have a way to easily free our stack once we're done with it. And now, though, we are going to get to the point where we're going to show you that this sort of whole aspect of using void star is rife with lots of possible foot guns for yourself. In this case, we're going to push both an int and an int star into the same list. That's really bad. They both look like numbers, but they have completely different meanings. One is a number like that we're using as the number, and one is an address to somewhere where a number is, right? And as I say here, this allows you to have heterogeneous lists, which is, as Lane makes fun of me saying, just a way to say you can have lists of different kinds of data inside of it, which is fine maybe if you're expecting it. Maybe in TypeScript you might write something like string or number this, but if you think everything's going to be a number, but some of them are actually addresses, that's a dangerous game to play, right? And as we'll see with many places in C, Uncle Ben had it right, with great power comes great responsibility. So in this scary double push, we're just going to show how easy this is to do this wrong. So the first thing we want to do is we want to say stack push, and we'll say S, and we want to push 13.7 on this. Now, we're just going to push the integer here, but C lets us say anytime we want, hey, that's a void star pointer. It's a void star.
it's void star, right? Even though this is just a regular integer, it's yeah, I'll accept that. You told me it is, I trust you. Even though in this case, we definitely don't want it to be. Then in the other one, we could go int star pointer, and we could malloc something for the size of int, right? And now we're going to push that onto here, stack push s, and we'll say void star pointer. So notice how here we pushed an integer, and this one we pushed a pointer to an integer. That is a dangerous game to play here because it's, what did we do wrong here? Let's see what we said. What did we write? What's the actual test doing? Stack S2 here, not pointer, null. Yep, must allocate a new stack. Okay, yep. And then we need to do pointer is 1024. Oh, I need to actually set this to do this. We need to say star pointer is 1024. We need to actually put a value inside like it told us to do, right? So we can run this now. And so this is a pointer to 1024. That's obviously not, that's not what we're looking for. That's a bad game to be playing. So this is where it's possible to shoot yourself in the foot very easily. I'll show some common things that I do later in this to sort of like help us out from making this happen all the time. But it's just something to be aware of that you can push these items into the same list. And now for the last thing that we're going to do with our stack, I want to show that it's not only like you can put just ints and pointers to ints in the same thing. You can put like literally anything inside of here. And the main reason I'm showing this is to remind you that C in a lot of ways just really doesn't care what you put in certain memory spots. It just lets you do it and treats it like bytes all the way down. Okay, at least that's sort of like for a practical purpose here. And void star basically releases C from caring or trying to promise to do anything correctly for you here. Right? So in this one, we're going to push a bunch of different random types into here. So first one we're going to do is we'll say like float star and we'll say like f pointer and we'll malloc a new size of float, right? And then we'll say f pointer is 3.14. Okay. And now we'll stack push s and f pointer. And it will say, hey, you need to tell me that you want that to be a void star. Very cool. And so now that we've pushed the float inside of here, we're instead going to be able to push the char star, right? We're going to push the string on here. So what we could do here is we could say something like char, and we could say like array, and we could do something like snake lang is blazingly slow. With an exclamation mark here. Okay, so this makes it so that this is actually, C knows the size of this because we do this with an array, not with a pointer. This is one option. So we could get like size t length is size of array. So that's one option. The other option we could do is we could go char star like s and we can say snake lang is blazingly slow, and then we could say size t length is stir len of s plus 1, right? Because we need to make sure that we have enough space to store the null terminated character here. Both of these actually work just fine because when we have an array before that degrades into just a pointer, C keeps the size. So I do kind of like this way, but we'll do this for right now just so that you can see sort of using stir len. So now we have chur stir, string, something like this, and we'll do malloc size of char, right, times length. Okay, so we're going to get the length, and then we'll go stir copy. We're going to copy from s into string, and then we'll stack push here the, whoops, I called this s and this s. Let's just call this value or something like this, right? So that we don't shadow variables there, which won't work. We'll copy the value here and we'll do this from string like this. We'll push this in. Okay, right? So just to be clear, we're getting the length of this. That's how many characters are in here. We need to allocate one extra spot for the null character, copy this in and push. And so if we give this a submit, now we should see that we've passed all of the tests. Okay, and now things get interesting. All right, now we're gonna make some objects in C. Now you're thinking, objects in C? That sounds terrible. Is it a boat? This object in the sea, get it? I'm sure Stas won't just leave me hanging here. He's gonna put a funny edit in there, I know it. I cannot wait for the YouTube comment saying, Stas left you hanging in chapter 9. Anyways, snakeling is just built in C. Right? We're not actually going to like make objects for C. We're making objects for snakeling. And when we say objects, we're just saying something like it
it can hold some data, like an int is an object or a float is an object. All of them are basically like unified in this one idea of being an object. And this data structure will, tell us what type it holds, how the size, if necessary, the data itself. And also for this round, we're going to build later for the first ref counting version, how many references to this object exist. And that's very important because we want to provide a garbage collected experience to Snakelang users because we don't trust them to write C. And so how are we going to do this? First thing we need to do, we're going to start making our snake object here. And so we need to make an enum. So we'll do type def enum and we'll say like snake object kind, and we'll put something inside of here like integer, and then we'll say that this is a snake object kind T. Okay, right? And now we need to make a union, type def e union, and we're going to say snake object data, and we're going to say v int, right? And it holds an integer. Oops, which should be int v int, like this. This is sort of like saying value integer. That's how I like to think about it in my head. And we'll call this snake object data T. Now we need to create an actual object, type def struct, and we're going to create snake object, and that's going to hold something like snake object kind T, and we'll call it kind, and snake object data T, data. And we'll call this snake object T. Right, so you can sort of see, hopefully, where the pattern's going to be happening soon. We're going to add new types to this integer. We're going to add new things to our union. And then we'll do the trick that we just did in advanced pointers with void star and all of this stuff to move between kind and data interchangeably. So if we run this, hopefully we get a compile. I spelled tipdef. Tipdef. Twice? Oh my goodness. That's a little rough. That's a little rough. All right, so now we've got our base types done. Let's work on iterating on this a little bit. So what do we have going on here? The first thing that we're going to do now is we're going to make our integer type and do a little bit more stuff inside of it. And the difference here is that C integers, right, they're just allocated on the stack. They don't know where it's being used, but we've got Chad Snakelang integers, right? They're going to be allocated on the heap and knows when it's being used, right? Because it's going to keep track of its references eventually. And this will become a lot more clear why we're doing this later. So just hold just a little, okay? And it'll make more sense once we start having variable size data. Trust me, okay? Just go along for now and we'll see where we're getting. So what do we need to do? First thing we need to do, we need to make a new snake object T obj, and we're going to malloc something that's the size of a snake object T, as we've seen ourselves do many times before. Obviously, if obj is null, then we're going to return null here before we accidentally access something at null. Now, what do we need to do? We need to set the kind to integers. We're going to go obj kind is integer, right? And now we're going to obj, and here's where we go data, and we'll say dot vint, right? Because if we go to here, we have this data here, and that's going to have a vint, right? Remember, it's a union. So all this data is going to get stored in the same spot. So we have to disambiguate which one we're going to do, and we'll set this to value, and then we can return obj here at the end. So now when we call something like new stake integer 42, we're going to make sure that we create a new one, store the value inside of here, and then that all works great. Let's go ahead and run that. And we should see a success coming in here. Great. So just to recap, create the new object, set it to the right kind, set the data in the right field to the right thing, and then return it. Now here is where we're going to start seeing why we're doing it in this way. Why are we creating these unions and these different fields? Okay, well now we're going to say, all right, instead of just having integers, we also want to have floats. And if we check object H, we're going to need to go modify some stuff here. Right now, all we have are integers, but we want to say, hey, I want to also be able to store floats in my language. So we can say this and we'll say float like this, right? We're going to put in a new float here. And now we need to say, hey, I want to have a float v float like this, right? So now we have the type or the kind so that we can know we have a float. And now we have a place to put that data. Both of those are important pieces, right? And now when we go back to here, we can do basically the same thing that we did here, right? We can put this here, but now instead of doing integer, we'll say float. And instead of doing int, we'll say here, and now we have value. So once we do that, we should see that new snake float. Oh, what did we do here? Oh, we need to add that we've created this function, snake object t star new snake float value, right? So now it's saying, hey, here's the way that you can make floats. And once again, we're creating functions here to really help us make sure that we're always initializing all the data correctly and doing the right fields and all of that kind of stuff. That's why we're writing functions to sort of encapsulate that data in the tools that we have available to us in C. All right, let's get to the next lesson. Okay. Now, though, things are getting a little trickier. Now we're going to do strings. And remember, strings, we are going to have to sort of have this additional allocation of what's going on, right? Strings are a different story than just ints or floats. We're not going to be able to just store them directly like this because we need to know ahead of time how big snake object data needs to be. So we can't just say, I mean, you could do something really bad, right? Like, char 500. Or like, well, as long as the string's less than 500, it'll work. Well, one, what happens when you want to store a string longer than 500? But also that means every time you make an object, you take up the 500 bytes here. That's a bad plan. So what are we going to do now? Right? We need to store a pointer to this. And so we're going to make sure we do all of that here. So we're going to add a new kind here that's called string, right? And then we're going to create a new char star v string value here. Okay, right? And then we'll also give ourselves a new snake object t star new snake string, which will take some star value like this, right? So those are going to be the things that we have going on here. Now, what do we need to do here? We're going to basically do a bunch of the same thing that we did before, right? So we can just copy this over because that's good. But here's the problem, right? Now we need to say that this is going to be string. And what are we going to do with this? We need to allocate the new memory equal to the length of the string plus 1. So let's go ahead and do that. We can say did we call it stir or string? V string, right? V string is going to be malloc, and we can say stir len of value plus 1, right? Then we need to check this. If obj data.vString is null, then we're just going to return null here, like this. Okay, now what are we going to do? We need to stir copy that in. So we'll do stir copy into the destination, which is obj data vString, and we're going to copy value inside of here. And then since that will work, we'll set the kind already to string. That's awesome. We're storing this inside of here, and then we return it. So if we give a submit on that, we should hopefully see that we are now successfully, right, both copying the value inside, right? So they're not the same data, right? We need to make sure we're copying the string as well as the string actually have the same things inside of it, right? So they're not the same pointer, but they've got the same data. And then we just make sure that it's the right size and all of that kind of stuff there. So that's great. That's our first one now where we're starting to do something where we're going to do additional allocation while we create the object. And once again, this is why we have to use a pointer here is so that we can actually store the data in the correct spot. All right, let's go to the next lesson. All right, now we got something fun though too. Up until now, snake objects can only hold like data to them to other stuff, right? Now we're going to create something where a snake object can reference another snake object, right? Like maybe we make 3 integers, we want to put them inside of a vector 3. So this is like a collection type, right? It's a type that holds other types. And this is definitely what makes garbage collection a little bit more complicated, right? And so what do we have here? We're going to do this for vector 3. We'll show you a little bit more later, and then you can kind of extrapolate if you wanted to make sets or dictionaries or whatever, right? So what do we need to do? Let's go to our snake object H. First thing we need to say is we need to forward declare this object T at the top of the file because now it can reference itself. Remember when we talked about declaring these, sometimes you need to do things like saying, hey, we're going to do type def, and we're going to say struct snake object T. All right, so this just says, hey, this exists. We will define later, right? Because we need this because what are we going to do now? We're going to create a new struct called a snake vector T, which we could put right here. Let's do that one right here. That's fine. So we can say type def struct snake, we can say snake object or snake vector. Is that what we're calling it? Snake vector. Yep. And we have something like snake object T star, because we're going to have a pointer to this here. I think that's what we want to do. Yep, each one is going to be a pointer, and we're going to say X, right? And then we have the same thing for Y and Z, right? So that's kind of like our 3 different spots in the vector. We have X, Y, and Z, right? And each of them points to a new snake object somewhere else sitting out here. And so now we need to make a new function as well, which is going to do snake object star T new snake vector 3. And that's going to have, we can actually write it like this maybe, snake object T star X, and we'll go Y and Z. Okay. And so now we have a new snake vector 3. It's got X, Y, and Z. We need to find a way to store this inside of our type. So we can say something like vector 3, right? And we also need to go down here and have a place to put this value. So we can say something like snake. Oh, whoops. I forgot to write this. Snake vector. And then did we call this vector 3 or just snake vector T? Snake vector T. So we'll say snake vector T, and we could call this V vector 3. Whoops, vector 3, like this, right? And so we can store this one directly. We don't need to store a pointer to this. We can store directly because this is going to be a fixed size of just 3 pointers wide. It's actually probably more efficient and better to do this. And did I write tipdef again? Oh my goodness. So that should hold our V vector 3. So now we have a place to store this. We have a place to write down this data. We have the kind to disambiguate it. And we have a new function that will be able to create this. Okay. And we don't need to make it a pointer to vector 3. It's directly allocated in the struct, right? It's just 3 pointers wide, which is not that different from 1. So it's okay. So in snake object 3, complete the new function. Okay, awesome. We're right here, snake object X, Y, and Z. What are we going to do here? Okay, we're going to do very similar to the ones that we've done so far, like this, where we take this, we put this in, we're going to return this. Now we're going to say vector 3, vector 3, right? And now we just need to basically copy these values in. So we can go V vector. Did we call it V vector or V vector 3? I've already forgotten. V vector 3, nice. Yep, that's what we're saying here. Dot X, and we could say that this is X. Then we can go Y and Z, and we can say Y and Z, like this, right? So now we have vector 3X is X, vector 3Y is Y, vector 3Z is Z, right? We're copying these values in, and they're pointers, so that's fine. That's pretty easy to do. And then we're going to return new object. So once we submit this, assuming I didn't write tipdef anywhere and I wrote typedef, we should get all of those working. And we are, let's see, void here should return null when input is null. Oh, I didn't see that was one of the things we wanted to do. If any of the inputs is null, return null. Oh, we can do that. If X is null, or Y is null, or Z is null, then we'll return null. That's great. We can do that for sure. Okay, let's try that again. Awesome. Yep, that just makes sure that we don't put null inside of any of these objects. We're making a vector 3. They should all have real values. Awesome. Okay, so that's our first one, where now we have references. We're going to explore this a little bit more as we go further. Now that we have a vector, which can always store the same size, right? 3 elements. The natural question next is, okay, but how could I store a dynamic amount of size? And then once again, you should be thinking, time to allocate some memory, right? So let's add a dynamically sized array to snakeling. We'll do this in 2 parts, right? Just so it doesn't get a little too crazy. First thing we need to do is go back. We're going to do similar idea to some of the stuff we've done here. We're going to say, okay, we need to add a new kind called array. We're going to put inside of here a new struct called snake array T, right? So let's go ahead and do that right here, which we could say typedef struct. And then let's go snake array T, like this, right? What are we going to put inside of it? We need to have a size, which will be a size T, size. And then we need to have elements, which will be snake object T, to a pointer, right? To a pointer, right? Which is, we're saying here, we want to say it's an array of snake object pointers, okay? And so that's where we're going to say elements, like this, right? So we make a new array kind here, and now we can put inside of here snake array T, we can say V array, right? That's our dynamically sized array. We also need to give ourselves this definition here, snake object T star new snake array, right? And right now, this is going to take in a size. That's all we're going to do. We're just going to say size T size. That's all we're going to do for right now, okay? So what are we going to do? Let's go and complete this function. We need to take basically a bunch of the stuff that we did before, like this, right? We can take this, we can just go paste it right here. We're going to do the same stuff, create a new one. We're going to make this an array. Awesome. We're going to accept a size parameter. We're going to return this null if that doesn't happen. Now we need to make an array of snake objects. So how much memory should we allocate? Like we said here, think about it. Probably the size of a pointer for each element in the array, right? Because we're gonna keep the pointer to the original object for all of the things in the array. We're not storing actual snake objects in the array, just pointers to them. That's important because we don't want to copy values. We want to get the reference to them, basically, right? So we can say this is array here. Now we can go v array. We could say malloc size of, and we can say snake object t star times the size, right? So we're going to get the size. We'll multiply those together. Now we get a new array. Of course, we need to check if obj data v array is null, then we're going to return null as well so that we don't access that. And in this case, right, this is actually one of the cases where it's actually a little bit nicer to put in a calloc instead of a malloc, right? And so let's change this to be calloc, which this just makes sure that we don't have anything inside of the array that isn't already nulled out, right? So it's all going to be zeros inside of here. The thing for this to remember is that these are actually multiplied, but these are actually 2 arguments for calloc instead of 1. So that's an important reminder here. And so now we need to set the kind, and we have this as varray, and now we can return obj just like we have here. And I think that's how we call calloc. We'll give it a quick run to make sure. Calloc operands to binary expression. Did I just do something wrong here? Calloc varray, calloc size of this, and size. Let's go ahead and just go look at, if we look at calloc here, we can just double check to make sure size, t, and size. Yep, so here's the number and here's the size. Oh, so we should have done this actually the other way around. It doesn't really matter because they get multiplied by each other, but that's okay. Size of snake star t, but this is a pointer to this, and this should be snake object t, like this, right? Okay, so when we do this, we're going to calloc this, and let's see if we remembered to do this right this time. Assignable snake array t to here, right? Okay, so that's fine. We can just say that we want this to be snake array t star. That's okay. We just need to explicitly cast that just so that we remember to do that. And then we need to dereference this here. That's actually not what we want to do because, of course, I forgot what I was doing. We need to say snake array t, and we're going to make this, we'll say something, like array, like this, right? We need to actually create the whole object. I forgot we were going to make a struct here that has size and the elements, of course, right? So we can do something like this, which is we could say snake object t star star elements. That's where we can do this, right? And we actually don't want to do this. We'll just go like this, right? So this is, let's get a list of elements here. We're going to calloc those. Then we're going to check if elements is null, then we'll also return null, right? We couldn't allocate these things. Now we can say this is dot size is size and dot elements is elements, like this, right? And now we can say that array equals this here. And then now we should be cooking. Oh, I did a semicolon, not a comma. Sorry. Okay. So what do we need to do now? If elements is null, if this can't be null, right? So we actually don't need that check anymore because we're actually creating like a struct this time instead of me just not paying attention. So that's good. So just to reiterate, because I know that we did a little bit of a detour there. I forgot that we were going to put this inside of an array, which is the smart thing to do because we need to keep this size parameter around. So first we try and allocate a thing of the right size. Okay. If we couldn't allocate it, we're done. Then we create our array data, right? And then we store that as the array and then we're done. And so that's good. We can hit submit and now we should be all set. We're going to make this array useful though soon.
So the first thing that we need to do is we need to basically define ways in making this useful of ways to set and get values from this array, right? So this is similar to how you might do something like this in Python or like this in Python, right? Where you're setting a value or getting a value. So we should have now inside of here, we have set and get already defined here. And what are we going to do? The set one is pretty easy here. So first thing we need to do is we need to check, hey, did you guys lie to me? Did you say, give me a snake object, but it's null, or value, and it was null? Okay, if either of those are true, then we're going to return false. False is kind of like saying, hey, this did not succeed. Okay, that's why we're returning false here. If snake obj kind not equal to array, then we're also going to return false. We don't know how to do anything with this if we don't have arrays, right? That's not the right thing. The next thing we need to do is we need to check, okay, if snake obj, let's say data.varray.size, right? If it's out of bounds, right? So the size, if we have 5 elements, what's the max thing that we can do? The max index is 4, right? Because 0, 1, 2, 3, 4. I counted that so weird. 0, 1, 2, 3, 4, right? Like that's how many we have. So if the size is less than or equal to index, right? And we're also going to return false, right? So if we had something like this was 5 and this was 5, that would work, right? Or if this was 10 and this was 5, that's definitely not going to work. And so now we finally can do this, which is we can go snake obj data varray.elements, and then we can say index equals value, and then we can return true. That's the only scenario here that this actually works, right? So we're going to set the elements index of this, and we need to do all of this checking to make sure we don't do something very bad. Now, similarly, let's check for get. This is going to be very similar here. We're going to check almost all the same things, except now we don't have a value, so we can remove that. If it's not array, we can't do this. So instead of returning null, we'll return false, right? And if this object is too far, we're going to do that. Otherwise, we'll do snake obj data varray.elements index like this, right? And that should be fine because varray, if we look at it, is allocated directly here and elements is there. So that should be good. Let's hit submit and see if we typed everything here. Oh, so close. I literally got bit by the semicolon bug. Oh, I thought I was going to have this first try. There we go. Okay, beautiful, beautiful, right? So just to be sure, this is just basically all the different conditions we could have where this would be an invalid kind of thing. Like, what does it mean to get something from an integer? That doesn't even make sense. So we're going to return null or set something on an integer. That wouldn't work. So now we have an array where we can actually set and get values from it, and those values are themselves snake objects. Now that we have a bunch of different kinds of objects, right? Integers, float strings, arrays, vector3, right? We want to do something cool to show how you could make a function like length in Python that can operate on multiple different kinds of objects and give you like a reasonable answer, right? So we don't know necessarily like the type of this ahead of time in Python, right? We just call length and then length figures out how to get the right value back. And so we're going to do kind of the same thing here, right? We have a new snake len. We probably need to add this here, or is it snake length right here? Yep, we've already got it. And so now here's what we're going to do is we're going to do a few different options. First one is we're going to check if obj is null. We're going to return -1. That's kind of like saying, hey, this is an error value, okay? If maybe like you could later propagate this up as an exception or something like that, but we don't have exceptions in C, etc. So it's like kind of like our way of saying this doesn't work, right? After this, we can just basically go and check all the different kinds of things that we have for the different data types for object, right? And so what I'm saying there is we can say something like switch, we can go obj kind, right? And we could say something like case, and we could say integer, right? And in this case, we can just return 1. If we have case float, then we return 1. If we have, and since we're returning here, we don't have to write break, right? Because it already leaves the function, right? If it's case string, then we can do return str len of obj data dot v string, right? Case vector 3, return 3. Case array, then we're going to do return
obj data.v array.size. Okay, do you see how we're sort of just writing each of the different scenarios here, right? And then we're going to return all of the value. And so otherwise we could say default could be return -1 as well, because it's like we don't know what that is. So if we submit this, we should sort of get, here's all of our different inputs, then here's all of the different outputs. And it actually is pretty nice to write a little switch statement like this. And then, in the future, if you added more cases, you could do that as well. So that's how we can start thinking about, okay, we can introspect the kind and then do different things. We're sort of like dispatching off the kind to do different behavior. We'll do another example of that in the next lesson. And here we are for lesson number 9, add. And so if you're familiar with Python, right, you'll know that there's kind of these dunder methods. They're often called double underscore methods, right? And the add method controls how, things get added together. Like arrays can be added together, right? And you kind of want different data types to act differently when you add them together. So in this case, integers, we would just add them, in arrays, maybe it's kind of like appending. So we're going to give the same kind of behavior here to our snake objects, all right? And this is going to take a little bit longer. This is the longest section because we're going to handle, as you can see, a bunch of different combinations. So let's just go ahead and get started and we'll work through each of these cases, right? So if we say A is null or B is null, okay, in that case, we're going to return null, right? That's our simple starting case. We need to make sure we actually have data. We're coding defensively here. All right, so now we're going to do this. And if you notice here, we have A integer, A float, A string, A vector, A array, or none of the above. So let's actually go, we're going to switch off of A kind here, kind, and let's write each of the different cases. So we have case number 1, which would be integer in this case, right? And we say, okay, what are we going to do? We're going to say, if B is an integer, then we'll return a new snake integer with the sum of the two values. Well, we already have some functions that can do that, right? So that's actually not too crazy hard. So let's switch off of B kind here. And this will be case integer. This is easy. Return new snake integer, right? What's the value going to be? We can go back to here and we remember, oh, we have new snake integer value. Awesome. That's going to be A data.v int plus B data.v int, right? That one's simple. If it's a float, then we're going to return a new float where we add these together. So we go float, right? This is switching off of B kind. We'll do new snake integer and we'll say, snake float, new snake float, and we'll cast our data here, float of A data v int plus B data. And this is important. You gotta remember to do V float here, right? Because that's what we're doing here. So we're going to return a new float with the sum of these two together. And then otherwise, default will be null. Okay, return null, like this, okay? So see how in each of these cases, right, we're gonna write out the cases, we're just gonna follow through, and we're gonna think logically about the combination that we have going on. So now we can go back to this spot here, we can go case float, right? And we'll do the same thing here. So we'll switch once again on B kind. And it is nice to be kind, by the way, which is good. So if this is an integer, what are we gonna do? We'll return a new snake float, right? And we're going to do the same idea that we had before, which is that now we'll do A data.v float, right? A is the float here, plus float of B data.v int, right? We need to cast int to float. If we have float, then that one's easy. New snake float, right? Of A data v float plus B data v float. And then otherwise, the default case is we don't know how to handle this, so we'll return null like this. Okay, so that's our first two. Those ones are the pretty simple ones, right? Those are the simplest cases. We just say, okay, we have an integer and a float or an integer float. We're just going to do that. Here's where things are going to get a little bit trickier. Case string. All right. So if B is not a string, then we're just going to return null. So that's basically like if B kind not equal to string, then we're going to return null. Right, which makes sense because we don't know how to add a string with an array or like a string with an integer. Those kinds don't go together. So we'll do this, right? So otherwise, we're going to get the length of the new string by combining the two strings, right? And that's going to be like this. So we'll say size t length is strlen of a data.v string plus strlen of B data, V string. And here's the tricky part, +1, because we need to keep a null terminator for these whole things together, right? So the length of the first string and the length of the second string, because now we know they're both strings here. We need to then allocate enough memory for this. Char star new string is malloc, right, of length. We can also, just to be clear, we can write char, we can write size of, whoopsies right here, size of char star times length, okay? Now we have a new string, and now we need to stir cat A and then B. So that looks like this. You just write stir cat into our new string with A, and then stir cat new string, new string B, like this, right? So now we're gonna basically concatenate this string into here, and then do it again, okay? And now we need to create a new string from this, so we can say like snake object T new stir. And this part is a little bit tricky. Stop and think about why this might happen. New string here, right? We'll call this one obj, like this. Why do we want to not just return this directly? It's because new snake string always copies, right? New snake string always copies. So since we're going to copy this new string inside of here, we need to make sure after we do that, we free new string so that we don't accidentally malloc this and leave it hanging around. And now we can do return obj like this. Okay, so get the length, make a new string, concatenate them together, create the object from that string, and now free it, right? Because we copy those. Okay, that's great. We already handled all the other cases. So now we can do case vector 3. If B kind not equal vector 3, then we'll return null again here. All right, so now we know we have 2 vector 3s. We're going to call snake add on each of the individual inside fields. So this is actually really cool. I love this because we can do new snake vector 3. We get to use functions that we've been doing thus far inside of this addition. Watch this. We can use the snake add function we just made. So this is snake add, and we can say a data dot v vector. I always forget, did we call it v vector or v vector 3? V vector 3, that's what I thought, just making sure. Dot x, and then b data dot v vector 3 dot y. Or sorry, x. So we're adding the x's together, and we're going to get a new snake object, which is the thing that we need to add inside of vector 3. It's like, when you're doing this, isn't that just awesome? It's so cool. This is like, you know, kind of making our own programming language here, and we're building up the addition constructs from the same constructs that we're doing before. We get to reuse them, which is cool. And so now we can change this to y and this to z, and we can go to here and we can change this to y and this to z, right? Because it's our x, y, and z. That looks good. And then our last one here is that if we have an array, case array, what are we going to do? Well, the other one also needs to be an array. So we do if b kind not equal to array. We're going to return null. And now we can do the same kind of idea here. We're going to need to create a new snake array that is the length of these combined, right? So we could say size t length is a data dot v array dot size. I think so. Let's just double check. It's dot size. Yep. And we called this one v array. That's awesome. And we need to add b data dot v array dot size like this. So now we can make a new snake object, obj, that's going to be new snake array of this length, right? Because we want to say, hey, give me one that's big enough to hold all of the elements in here. So now what do we need to do? We need to iterate over all of the elements in A and then B and set them into the new array object. So we can do something like this. You need to do for int I equals 0, or we could do size t, I guess. I less than a data.v array.size, I plus plus. What are we going to do? We're going to say, did we call it snake set? What did we call this one? Snake array set. Yep. So we'll do snake array set. Snake array set. And then what are we going to put inside here? First one is our new array. That's this one. Obj. Then what are we going to put inside of it? At this particular index. So that will be I. And then what are we going to put inside of it? We need to get a value.
that's going to be snake array get, right? And we're going to say the original array, a data.v array. This is actually just an object. So we can just say a, and then we can say here, what are we going to set it to? I. That's what we're going to do. So now we've done this, right? This is basically going through and saying, all right, for each of the items in this array, set it to here, right? So we're copying those over basically, right? And then what else do we need to do? We need to do almost the same thing. Almost the same thing for B. This is where it's going to get a little bit tricky, right? B, but we need to say, instead of I here, this is going to be I plus a data.v array.size, right? Because we need to offset where we're setting these. If you think about it, we like fill up the first 5, and then B needs to copy into the last 11 or something like that. That's actually it, right? And then we need to actually go here and just, return the object. That's an important piece here. And then the last thing is default. We just return null like this. Okay, so we're not going to actually do subtract, multiply, or divide, but like they would be exactly the same pattern, right? Where you would write out a bunch of things and do this. And did we type everything perfectly? Oh, there was a close one. Almost for sure didn't. Did we miss any semicolons? Ooh, it's an easy one to miss when you're not using anything with LSP. Okay, here we go. Okay, yep. All right, ready? I think we got it first try. Oh no, I was so close. All right, what did we do wrong? What didn't we do? Should concatenate 2 strings. What did we do wrong here? Let's go to our strings. We messed something up in strings. Oh, we were so close. Okay, case string. If b kind's not string, return null. Yep. We're going to get a data v string, b data v string plus 1. Yep, we're going to malloc those. Did we do strcat wrong? Did we write down strcat inside of here? Allocate memory for a new. Oh, of course, instead of doing malloc, we need to do calloc. Of course, I forgot. That's probably our first one here. Let's give this one a submit and see if that solves our string problem here. Oh, I was hoping. All right, let's read again. What are we actually getting here? String expected data v string hello world, and we got not that at all. Should concatenate strings. So I'm thinking strcat might actually go this way. But let's go check here. Strcat is destination and source. So I would have thought, oh, of course, I'm a fool. Oh man, we don't want to copy in the data from here. We want to copy in the string. Like an absolute fool. I'm sorry. I missed that one earlier. Okay, that's good though. That's good. Yep. And then we knew that array was already broken. So let's figure out what we messed up here. So this should be, we need to create a new snake array of the right length with a data v array size, yep, and b data v array dot size, yep, that part's good. What do we need to do now? We need to set this, this needs to be b. Of course, I was too busy with my copy paste. We need to actually get the values from b. Okay, there we go. We got it. I'm pretty sure. This is why testing is so nice. We were so close. Oh, I wish I would have gotten that first try, but I'm not going to redo it because I like it to be a little authentic that way. Let you guys struggle there and see what's happening. So that's it, right? This sort of idea, you could imagine extending it for subtracting, multiplication, dividing, any kind of thing that you would want to do. You could build up these kind of behaviors over all of your objects and then give them custom sort of things to be able to call, length or add on them. All right, it's time. Garbage collector time. What is a garbage collector? In C, we've been manually managing our memory, which is not only difficult to do, but tricky to say. I always feel like I'm going to make a big mistake while I'm talking about it. However, that's not the only strategy for managing memory. There are alternatives like the Rust strategy, which uses a borrow checker, which, while still including sort of manually managing the memory, truly the Rust compiler is the one that determines whether an object's lifetime is complete or not, and if so, it will free that object. However, a garbage collector is quite different. In garbage collection, the language itself, for example, Python or JavaScript or Go, determines if a particular object or value is still live. Live means that the value could possibly be useful. If we had a variable that was created inside of a function, and then the function returns without referencing that variable anymore, we want to give that data, that memory space, back to the operating system. In that case, we would consider that object no longer live, right? Because there's nothing that could possibly reference it. It's useless. And in garbage collected languages, it will figure that out automatically for you. However, it's not free. The garbage collector still has to use some algorithm to determine what values are still alive or not. And like many other languages, for example, in Python, a lot of Python is written in C, or at least one implementation of it is in C Python. That garbage collector may be written in a different language. So let's talk about some of the algorithms that are useful for garbage collectors to determine whether a particular value is still live. The first kind is called reference counting. Reference counting is probably the simplest version of garbage collection. And what it is that every object has an additional field that is its count. And when you create the object or some other variable references the object, consider something like a list. If I have a variable foo and I put it inside of a list, okay, well now the reference count for foo might be 2 because it's 1 for itself and then 1 for this list. Now, when we remove that list, or maybe we pop that element out of the list, we're going to drop its reference count by 1. And maybe if we return from the function that created foo, now its reference count might drop to 0. Once an object's reference count drops to 0, then we give that memory back to the operating system. Naive reference counting has some downsides, like an inability to track cycles, and it is quite expensive because every time we do an operation, we have to go modify all of the objects that we're touching. Because of that, people thought of other strategies. The other primary one that we're going to cover is mark and sweep. Mark and sweep is an idea that we'll be able to find all of the variable that are directly referenced by our stack frames, generally speaking, and then we will trace through all of the connections of those variables to find any other ones that are referenced by the roots. Once we've done that, we'll be able to determine, aha, I see all of the set of variables that are directly referenced and indirectly referenced, so any of the variables that are not marked, we can sweep those away. Really, the sweep is actually the search, but I kind of like to imagine that you sweeping them back to the operating system. Mark and sweep is a bit more complex, but it can handle certain cases that at least naive reference counting can't handle, like a list who references another list, who references back to the original list, which, see, that's a cycle. That's a problem for reference counting. You'll never get down to 0, but for mark and sweep, if none of the roots touch either of those lists, we'll be safe to mark them as not alive and free them and give them back to the operating system. Additionally, mark and sweep doesn't require us to do operations every single time that we touch or reference a variable. We only have to do the work when we do something often referred to as a GC pause, a garbage collector pause, where the garbage collector is going to do some work to go check which variables are still alive. One of the key things that I'm trying to emphasize here is that garbage collection is not free. There will always be some work for the language runtime to determine, is this particular value still alive or not? In languages like C, the programmer has to do that ahead of time and hopefully remembers to do it correctly. Or in Rust, maybe the compiler does some checking for you to let you know that. But in garbage collected languages, you pay that expense at runtime rather during development time. That's one of the trade-offs you have to decide when picking a language, is where do you want to pay that cost? So, garbage collection. This is what you've been using in all of the language up till now in boot dev, or if you're not on boot dev, promo code TEACH, by the way, of course, then you've been maybe doing this if you're writing Python or TypeScript or whatever, right? All of these things have a garbage collector. They manage the memory for you. As we've been working through the course, we've been talking about when do we need to dynamically allocate memory and free it and all these other things, right? And so it's always some sort of malloc and free or new and delete, whatever, right? And there's actually different ways to manage memory. You know, Rust has the borrow check
checker, which is sort of like at a type level malloc and free. There's a little bit of, wiggle room in some of that. Or other languages, maybe like Zig or Odin, give you access to allocators. So there's a bunch of different ranges of manual memory management and automatic, right? And in this case, we're talking about garbage collectors, right? And garbage collector is an automatic memory management where you just don't have to think about whether you're using an object anymore. It will get cleaned up later. And it also makes it so you can't access something that's already been freed. That is like another common problem in C is you think you're all done with an object, you free it, and then you have this problem called use after free. So one of the examples we gave is Go in this course of a garbage collector. So we can click Go and we can keep moving on there. So we're going to implement the simplest garbage collector sort of like pattern first, which is called reference counting. Reference counting is basically exactly what the name is. Once in a while, programmers get it right, which is that we keep a count of how many times this object is being referenced, right? Whenever something references it again, holds on to that reference, we increment the count. So you could think about like when we put it in an array, we're going to have to increment the count of like some integer so that we know that it's getting referenced. So if we lose one reference, we don't throw it away. So the object inside the array is gone, right? If that makes sense. So we're going to keep on incrementing this count and keeping track of it. And then when we're done, we're going to decrement the count. And when it gets to 0, we will automatically free it. So that's the cool part of reference counting is the algorithm's very simple. We're just going to keep track of how many times it's counted. And when it gets to 0, we'll free it. So we need to modify our snake object kind here to include a ref count value. So we can just say int ref count, something like this, right? So that will now give us our ref count value. And then when we go to snake object C, we need to do something special here. This is the tricky part. We've already abstracted away this so you don't have to go fix it in like 25 times for wherever we create a new snake object. But new snake object needs to do something important. First one, snake object T obj is malloc size of, you got it, snake object T, right? So we need to first allocate a new snake object. Awesome. Now what do we need to do? Of course, if obj is null, we're going to return null here. All right, now what are we going to do after this though? We need to set obj ref count equals 1. We're going to do that because now we're saying when we create this object, it has a reference, right? This just makes it a lot simpler when we're keeping track of this. Like we brought this into existence, it has a reference. Then when we're done with it later, we'll sort of decrement that count. And then we return the object that we just created. So that part's pretty simple. We're not doing any of the actual collection yet. We're just setting up the ref count so that later we can use it. So since we have that ref count though, let's start using it. We need to create a ref count increment function. And right now it's pretty simpler. It just increments the ref count, which is basically doing nothing. So if obj is null, we're just going to return. We're not going to do anything. Otherwise, we'll do obj ref count plus plus, right? We'll just increment the count and move on. Nothing too exciting happening there, but we do need to have this function to keep track of what's going on. A little more complicated than incrementing a number, not very complicated, right? Is now what we're going to do once we've gotten to the point where there are no more references, right? So when we decrement a reference, right? What we're going to do is, it starts pretty simple, right? We're going to, check if it's null. We're going to subtract 1, blah, blah, blah. But then once we do that, we need to check if there are no existing references left, which of course means checking if the ref count is 0. And if so, we're going to automatically call this ref count free. That's where the automatic memory management really comes into play for us to be using. So let's work through this and then we'll start to see. At first, we're just going to do this for integers, floats, and strings. Those are the really simple object types. Those are the ones that we need to think about first. So let's try and do this, right? The decrement code is going to be the same for all types, right? Which is if obj is null, then return null. That one's easy. Okay, what else are we going to, or we'll just say return. What are we going to do after this? We'll say, okay, obj ref count minus minus. But now we need to say if obj ref count is 0, then what are we going to do? We're going to call ref count free on the object. Okay, so this is going to make sure that we're freeing all of the things associated that we need to for this object. So let's look at this. Let's switch Based off this, we'll once again do if obj is null, just in case. It's a little good to be pretty defensive in C. Now we'll do this. Switch obj kind, just like we've been doing before, right? And we'll say case integer. What are we going to do? Free the object itself. We don't need to worry about any data inside, right? So this one's pretty easy. We just say free obj, right? Case float. We're going to say free obj. Nothing crazy there. Here's where things get a little more complicated. Case string. All right, we're going to free. What do we need to free first? We can't just free the object. This will be bad because after we've done this, we're going to like lose our pointers and other stuff like this. We need to first make sure we actually free the underlying data, which would be free obj data v string, right? We need to make sure that we're actually handling this scenario. And in each of these cases here, we also need to make sure that we do something like where we say, break like this, or even we could potentially do, return free or something like this. We'll write it this way just because this is a good pattern to be having for doing this. We'll say break for right now in case we need to do any handling at the end. And then we'll also do here, we'll say break, okay? And right now we don't have any other things going on and we don't need to do anything at the end of the function. So this should hopefully work. We do notice that each of these has free obj, free obj, free obj. We could potentially try and do something where we put this down to here. And you could do this. So then each of these is just break like this, and then break like this. That also could work just fine too. So let's hit submit and see if we wrote that in a way that makes sense. Beautiful. All right, now we're going to handle some of the more complicated cases coming up next. All right, now let's handle our first container type. Remember, container type is something that can hold references to other objects. So in this case, we have vector 3, right? Vector 3 holds references to other snake objects. It references them through its X, Y, and Z fields. So when we create a vector and place objects in the field, we need to increment the ref count to each of these objects, right? Otherwise, we are not going to keep track of them appropriately. So update new vector 3 function, and we're going to ref count each of the objects here. So I would put this, if I were thinking of it, I kind of would like to group this with where we're storing these inside of here. So I would go ref count inc X, ref count inc Y, and ref count inc Z, right? So we make sure that we increment the reference count for all of those. The next thing that we need to do is that when we get to this case here, so when we free a vector, you should just be thinking about it, right? A vector has its X, Y, and Z. So when we're like saying we're done with this vector, we need to subtract 1 from the reference count of all of the objects inside. So that's actually pretty easy because we can just go ref count dec obj data dot v, obj data v vector 3. Oh my goodness, I've literally written this 5 times already today. V vector 3, there we go. Vector 3 dot x, right? And we're going to do the same thing for y and for z, so that we make sure we decrement each of the counts. This is very important because if we don't do this, we're going to leave these counts hanging forever and we'll never free the objects. So instead of actually automatically managing the memory, we're just not doing any management at all. So just to reiterate, we increment the count when we reference them, and then when we're done with this vector, we free them all. So now we can submit that. And now we're starting to see like how these container types are working, and we're able to track the reference counts across different kinds of objects. And now that we've done that for vectors, now we need to do it for the dynamic version, which is for an array. So in this one, we don't have to change anything for when we create a new snake array, right? Because, when you think about it, we create it empty and then we fill it in later. That's how we have stuff here. But we do need to update when we set a new value, right? In here, we have each of the examples of what we've done here. And the thing we need to track now is when we put this value inside the array, right? We need to make sure that we increment the count. And the trick here, the thing that's a little bit goofy, right, is we also need to make sure we decrement the count
of the previous object. That's a really important aspect of what we're doing. So how are we going to do that, right? We need to make sure, number one, we increment whatever the current value is. So let's go ahead and do refcount our new value, right? That makes sure that we are keeping track that we're about to save and do something with this value. Then what we need to do is we need to check if, and let's do snake obj data.varray.elements index not equal to null, right? Because if there's an object here, then what do we need to do? We need to say refcount this thing here, right? So we could also save this as like old value or something like that, but we can also just copy paste this in is fine too. So if we do this, like this, then we're going to decrement that count. And now we can save this value right here. So that lets us make sure that we're adequately keeping track of items when we save them in an array. And now we need to also update similarly to how we did this here with saving a vector and ref counting each of these. We need to go here for array, which would be case array like this. Let's put these here, and we need to do exactly what it's saying here. We're going to iterate over each of the items. So for, int I equals 0, I less than, we can do like, let's do snake array t. Array is obj data.v array. We can say array.size I++. What are we going to do? We need to check and make sure by doing ref count and we can say array.elements of I like this. And the nice thing is if we go to our ref count here, if it's null, then we don't have to do anything. So we don't have to double check if it's null inside here or anything like that. We can just know that since we're calling this, it will be safe, even if we've never set anything in those locations. And then now we need to free obj data v array, v array.elements, like this. Right, we need to make sure that we actually free the array itself, because otherwise we're going to be in trouble because then we left this empty, right? So remember, our elements is this array of elements that we allocate when we create a new array. So just to reiterate, each item needs to be decremented, and then we can free the array itself. When we run this, we should see that we get all of our tests passing, which is great. And now sort of the last bit here is just a little review of what's going on for ref counting, which is that we basically encapsulated the entire garbage collection logic, right, into this new object function and then an increment and decrement. It's really nice. Nothing needs to change in our like snake add function. This would still work because anywhere we create a new integer or we put something inside of a new vector or we append arrays using these, we've already kept track of the fact that we are incrementing a reference to this object here. So it's really cool how this garbage collector basically gets constructed up from this really simple idea of adding and subtracting one from the reference count whenever we do this. So in this case, the question is, why doesn't the snake add function need to take care of garbage collecting the resulting object, right? When we do snake add here, something like this, is because we're going to return a new object, right? This is going to happen whenever we ref count this to 0. And definitely not this and definitely not that. So that's our answer. And that is it for Refcounting GC. We are going to be starting now, Mark and Sweep, our final boss of the course. So in the previous chapter, right, we built our reference counting garbage collector, and it can handle, simple types, some dynamically allocated type, static, and dynamic container types, which is cool. It's just a little problem. Let's consider this. We make an array, we make another array. We put the first array in the second one. We decrement the first one, we decrement the second one, and it says, hey, okay, sure, there's nothing here. Shove the second array inside of it. Everything works. But the problem is, what happens if then we put second inside of first as well, right? We're going to run into a problem that we cannot solve. We are going to have a cycle. Ref counting, the way that we have it, can't handle cycles, right? This is simple because right here, we don't have a cycle yet. But let's look at some of our examples over here. Let's run this. Notice the assertions fail.
even though first and second both have had theirs decremented, right? First and second, you would think, okay, that seems like it should be done. But it's not true. It's not true, right? We need to update them so they update and they match the sad reality. They should both be 1, right? They should both be 1 now because they're holding references to each other. Like a circle. This one's referencing that one, which reference this one, which reference that one, which reference this one, which reference that one. That's a problem, right? We're never going to drop it to 0 and we'll never free the array. So we have a cycle. And the garbage collector we built so far cannot handle this. Hopefully, we can come up with a solution. So the solution that we're going to come up with is a mark and sweep garbage collector. And let's talk a little bit about what that actually means. So a mark and sweep garbage collector can detect cycles, which is good because that can prevent memory leaks in these cases. It's also in general probably like more efficient, right? Because instead of every time we like reference something, we have to go and update all of the values of like these integers, right? Like anytime we change something, we have to increment or decrement a number. That's expensive. We need to go all over the CPU, or all over memory. We need to change all these values. Not good. Because remember, when you're thinking about it, right, a garbage collector is just wasted work, right? It doesn't make your Jeopardy wrapper run any faster, right? Instead, it's just wasted work. Whatever the garbage collector is doing is wasted towards the end product that you're actually shooting for. So if you can make a more efficient garbage collector, that's good. More of the CPU is actually spent on useful work. And there's some other problems like, if you had multiple threads, if you use ref counting, you have to use atomics, which will require CPU synchronization, a bunch of other stuff that like maybe you don't really care about normally, but do really matter in like real world performance. But there are some cons, of course. This is going to be more complex. Okay. This is going to be more complex. You're going to have to stick with us. I promise it's going to be cool, but it's a lot more complex than add number minus number. Okay. Other problems is like, because you're going to kind of collect a bunch of things at once, if you need to do a lot of garbage collection work, you might have a point where like your server is only working on garbage collection, which is not great. There's more memory going on and it's a little bit less predictable, right? Because it can vary what's going on. So we're going to make a new virtual machine type. This is sort of what's normally tracked if snakeling were a real functional interpreted language. And I mean functional in the best way, which it's not, right? But this is sort of a like placeholder we're going to have that represents the kinds of data you would need to keep track of if you were doing a programming language. We need some place to store the current state for the garbage collector. And, if you made it this far in the video, you can always spam Lane and say, let's make a write your own programming language course on boot.dev, which Lane is saying we don't want to do that. Yeah, there's that would be a lot of work, but it could be interesting. So let's take a quick peek here at vm.h like it says and look at the vmt struct, which is going to say that we have a stack T, the thing we wrote earlier, of frames and objects. All right. And we've already talked about what frames are, right? They're stack frames. When you think about something like scope 1, scope 2, scope 3, each of these kind of like scopes here enters a new stack frame. And we need to keep track of what things are referenced within each of those frames. And the things that are referenced are the objects. So at each one of the scope entrances, in this case, function calls, right, a new stack frame is pushed onto the frame's stack. That's this guy right here. And because we have void star to work with generics in C, you can't really tell what type of data is in the stack T. So we're going to write some wrapper functions to avoid the foot gun scenario where we accidentally like put an object into frames or frames into objects. It's bad. So don't worry, we're gonna handle that later. And the objects field is also a stack and it just holds snake object T pointers, right? So what we need to do is in VMC, we need to allocate some new space for a VMT. So we can go, let's go VMT star VM is malloc size of VMT, right? Of course, if VM is null, we're gonna return null again, the classic. And then what we need to do here is we want to create frames with a stack capacity of 8 because we're just sort of going to automatically give it some size initially so we don't have to do a bunch of thrashing with the operating system. So we can go VM and we call this frames, right? So we can say frames is equal to stack new 8, right? And then we can do the same thing, VM frames is null, then we'll return null again. Really here, then we should probably like free, okay, fine. We'll do it. We'll say, free VM, that's fine, right? Because we need to make sure that we're actually handling this. Then we'll go VM, same thing for objects, stack new 8, and we'll do if VM objects is null, then we need to make sure we free the VM and return null,
right? Otherwise, we're not going to do it. And now we can return the VM. And we also need to do the VM free. And so that should be, we'll do stack free VM objects. Oh, it will also, of course, if VM is null, return, just return. That's good. So then we have stack free VM frames and stack free objects, and then also free VM, right? So we're going to make sure that we're freeing our frames completely and our objects. Later, we'll make sure that we appropriately clean up any of these items that are inside. So with this, we should be able to run this just fine and get that result. So that's the very first step of creating our virtual machine. The next step that we're going to do is we're going to try and solve the problem of, hey, it's super easy for us to accidentally create data that makes no sense by pushing void stars into the wrong places. So we're going to create a little bit of type safe wrappers around this. Like in this case, remember we said stack pushing onto frames like 7. Very bad. We're going to make something to make it a lot more difficult to make a bad mistake, which is we're going to do this VM and sort of say that the top level thing needs to be a frame T. So we're going to do that, and we're going to start pushing these inside. So we want to create a VM frame push, which is going to take a VM and push a frame onto it. So we should do if, VM is null or frame is null, then we'll just return, right? Otherwise, what are we going to do? We're going to say stack push VM frames, and we'll push the frame onto here. And we'll just, for clarity's sake, we'll just do this like that, right? So now we have pushed onto the frames this new frame. That part's pretty easy, right? It's just called stack push on it. When we create a new frame, this is a function that we're going to use in a few other places to get back a new frame T. So we can go something like this. We go to our VMH, we look at a frame. What does a frame look like? It has a stack of references. So we're going to need to do something like this. We're going to say, all right, I need to make a new frame. Frame T star frame is, let's make a new one, which is going to be malloc size of frame T. And then if frame is null, then we'll return. All right, what are we going to do after that? We need to say frame references is a new stack, right? Frame references is a stack new of size, what are we doing, 8 again, just to give it a little bit of help there. And we'll check if frame references is null, and then we'll have to do free frame and return null. Okay, so now we've got this, and now we need to do the thing we just did here, which is VM frame push, and we'll say VM and our frame, and then return frame. This makes sure that we can't actually, we're not going to create a new frame and then forget to actually associate it with our virtual machine. So that's great. And then the last thing is we need to frame free. So we can do if a frame is null, then we'll just get to return here. What are we going to do after that? We'll say stack free frame frame references, and then free frame. Right, so now we've got our way to clean up the frame as well. So that's going to make sure, whoops, what did we do? What did we forget to do? Right here, this needs to be null. Yep, that makes sense. So when we do that, that's going to make sure that now we're going to type safely work with our virtual machine and our frame so that we don't accidentally shoot ourselves in the foot by pushing the wrong thing onto our stacks. The other key thing, besides just keeping track of the frames, is we also need to keep track of all of our objects. We're going to do this because we need to know every object that exists so that later we can mark and sweep them, which we'll explain when we get there. So instead of keeping track of how many times things are referenced, we're instead going to keep track that an object exists at all, right? So we're just going to treat, is this thing referenced or not? So in VMC, it says create the new VM track object, which this one's pretty easy. If VM is null or obj is null, then we're going to return. Then what do we need to do now? Now we're going to stack push again. We're going to make sure that that would be possible to do, and it would be very bad. So we need to do objects void star obj. Okay, does this make sense, right? If you're thinking about this, we need to make sure that we only push this onto the objects, and this keeps us safe from doing something stupid here. And if we go back to snake new, now we need to say something here where we would say VM track object, and we're going to say that for the VM and the object. That's going to make sure that everything we do here is safe before we return it. So if we submit this, this will now double check and make sure that each of them is contained inside of here. In this one, I do want to look at these tests a little bit, which is just going to show, hey, when we create a new object, that gets put into the objects stack that we're using for our virtual machine. That's important. That's important to make sure that that's the case. So we'll go on to the next lesson. So now we need to look at how we're going to be doing freeing with snake objects, right? Before we had this ref count free, and that did a bunch of work to check the different counts and all of the other stuff here. We have a kind of a different idea now that's coming up, right? So we need to rewrite our freeing logic for mark and sweep. So in this one, since we're already tracking all the objects, we don't need to do this ref counting work at all. That's what's happening by mark and sweep when we get there. So there's some cool tricks coming up for mark and sweep to manage this, but for now, just trust me, we're gonna get there to make sure we've correctly done everything. So for each of these in Snake, we're gonna complete how this works. So for integer, float, and string, we don't need to do anything special, except that string, we need to make sure we still do free obj data v string, right? We free the string itself. For vector 3, it literally doesn't need to do anything. Once we get rid of this object, it's going to be safe. And array needs to do one thing because we've dynamically allocated memory here. We need to make sure that we go free obj data v array dot elements, right? This is what we need to free to make sure now that this array that is dynamically allocated has been freed. And so now when we go to VM free here, what are we going to do? This is the beginning of what's going on. VM free is going to make sure that we actually go and do everything we needed to do here, which is number 1. We're going to iterate over all the frames and free them using frame free. So we can go for int I is 0, I less than VM frames dot size. Oh, okay. We'll also do this. Return. We're just return. Okay, just to be sure. Frames size. What are we going to do? I plus plus. We're going to say frame free VM frames dot elements I, right? Because we need to make sure that we're accessing the elements of this array. Cool. Now we need to go over and we say for int I equals 0, I less than VM objects dot size I plus plus. What are we going to do? We're going to say snake object free. And for that, we just need to do VM objects dot elements I as well to get back that object here. And then at the end, we just need to make sure that we're going to free these stacks. So we can say stack free VM frames and then stack free VM objects. And then now we can just free the VM itself. Okay, if we got that first try, that's going to be pretty cool. So let's try submitting this and making sure that we're doing everything there that we said. VM frames dot elements. What did we do wrong here? Did you remember to do this? VM frames dot elements. Let's check what our type actually is for these because I don't remember. If we go to VM stack h VMH here, we have stack. Oh, this is a pointer to those, right? Okay, yeah. So we just messed that up by not doing elements like this and like this. And that just makes it a little bit easier to do. All right, that should now work because now we're using those. And no member size in struct sac. Did we call this count? I think we may have called that count, didn't we? Count. Sorry, not size. We called that count. Cool. And we should be able to run that just fine. And we didn't call it elements because we called this data. I'm sorry. That was, elements was for our array. Of course. That's why I'm getting confused. This is data. There we go. Okay. That should work now. Because I was thinking of array, not our stacks. Okay. It's okay. We're good. There we go. We got everything passing now and we're good. So this is going to allow us to free both the virtual machine itself, the frames inside of it, and the objects. But just because we can free them doesn't mean that's all we need to be able to do. We need to mark that certain objects are actually referenced by a frame. If we go back to our virtual machine here, we see that each frame has a stack of references. These are objects that a frame references. And so this is actually pretty easy, right? We just need to make sure that this puts an object into the stack of references for the current frame. So we can do something like this. If a frame is null or obj is null, then we'll just return. All right, what are we going to do after this? We're going to say, okay, I have this frame here and I have references, right? References is this stack pointer. So I say references. I want to push this on here. So we can just go stack push this void star obj like this, right? We're going to push this object onto the frame's references. That's pretty easy. That's the nice thing about writing functions is we don't have to repeat ourselves too much. And now once we have this, we're going to be able to go ahead and start doing our mark and sweep algorithm. The algorithm that we're going over here is actually quite old. It's pretty cool. John McCarthy, 1960s, managing memory in Lisp, the parentheses language. It's the same amount of parentheses as other things, but that's a talk for a different time. So it's basically two primary phases. First phase is mark. So we're going to walk over all the objects and we're going to see, okay, what objects are reachable. So if there's an object that literally nothing references, okay, then that's going to be important. And then after that, we're going to sweep by scanning through the memory, collect the unmarked objects, and garbage collect them. So what's cool is this time we don't have to keep track of how many times a particular object is referenced. Instead, we're just keeping track of if a particular thing is referenced. So this is kind of like a mindset shift as we're going through here. We're just going to like walk through these connections of objects and then see if something is used or not. So let's get started here. We need a few more little bits of information to keep track of these. So first thing is in snake object H, where we have this. Instead of having int ref count, right, we're going to have bool is marked. Okay, that's the first thing that we've got here. And now in snake new.c, when we create a new object, we're going to make sure that we put inside of here, obj is marked is false, right? We need to make sure that when we start, we set that to false to be explicit. When we run this now, we should see that none of these objects are marked and that we're able to pass all of the tests. That's great. Mark! All right, so in some mark and sweep implementation, you see different ways to mark root objects. These are basically like the things directly referenced by a stack frame, right? Like if you have A equals 5, A is obviously referenced by that stack frame directly. So we can consider that kind of like a root object. In our way that we have the VM set up, it's pretty easy to just find and mark those, and we'll test those out in a second. So first thing we're going to do, we're going to start writing our mark function here. And it's just that every object that's directly referenced by a stack frame to is marked equals true. Okay, that's not so bad, right? If VM is null, whoops, return. All right, now what are we going to do? For int I is 0, I less than VM frames count I++. So we're going to go over each of the things in here. So we could just write something like frame. This might be a little easier. Frame T frame is VM frames I. So we have the frame here. What are we going to do here? We're going to say, okay, let's check all of the objects that are referenced here. So for int, we'll say j is 0. Maybe we'll just say like object, we'll just say j, it's fine. You guys know what I'm saying, is 0. I less than frame referenced count, j++. I almost did it. I almost did the classic mistake there. Almost why you want to say that instead of I and j. What are we going to do now? We're going to say frame referenced. And then instead, this is going to be not elements. That was the thing I did last time. Data, right? Data j dot is marked equals true. Ooh, but this is actually a pointer to here. That's important too, because we need to make sure we're updating the original item. So we're going to say, okay, I've got my frame. What's referenced inside of here? Okay, whatever was referenced inside, we're going to set it is marked as true. So if multiple frames reference this thing, that's totally fine. We're not incrementing a count. We're just marking whether something was true or not. So it should be, if we go to our test and we look at this, right? We like mark something here. None of these are going to be marked, right? Teach skill, lane skill, not going to be marked. But if we reference both of these objects, then they will be marked. And then similarly here, if we don't reference some of them, then we won't have that working. Oops. What did we do wrong here? Frame T struct is an expression stack T. Oh, right. Sorry. This is a stack. The stack is we have a frame here that's holding these items. Oh, no. Sorry. I didn't do frames. I did the wrong thing. Cancel. I already know what I did wrong here. I didn't say data here. That's the thing that we're trying to do. And then this is actually a frame T. Yeah. So that was because we forgot to access from the data. So that's good. When we have this frame here referenced, it should be, did you mean references? Ooh, I do mean that. Thank you. References. Like that. Just a typo. That's fine. And then now we have is marked. Base void is not a struct or union. Oh, true. We need to say something like this. Because it's a void star, we need to do something instead, like saying snake object T obj is actually all of this here. So we need to say this. You could just cast it directly, but I find it a lot more confusing to do it that way, because we need to tell C what kind of struct this actually is, right? Because it only knows that it's a void star inside of the data. And once we do that, we're all set. So now we have our very first part, which is we're able to mark all of the directly referenced objects. All right, now that we've finished marking, we can trace through everything here. So let's think about this example here. Let's say we have something like A equals 5 and we return a list with A. So if we run this code, right, with A inside of it, once we leave get list, once we're out of this stack frame, A is not going to be directly referenced. But obviously we don't want to free it yet. It's inside the list that's returned and put outside of this stack frame, right? So we need to make sure that when we free, we don't free A too early. Otherwise, our list is going to be containing elements that are already freed. That's really bad. We can have other problems here, like where we make A, we append A to itself, and we return something completely different. In our old reference count version, we would never be able to free this, but in this one, we're actually going to be able to, as there's nothing ever left that holds this A value. So let's think about how we're going to write our trace function, right? So it's going to look for any objects that's referenced by any other object. If we can find it referenced by a root, we're going to consider it alive. And if we can never find it referenced, then it's going to be unreachable, which means later we'll be able to free it. So tracing is part of the mark phase of mark and sweep. And so this is where we're marking all the objects referenced by our root objects. So this is once again going to be one of the larger ones. Take your time, follow along, pause if you need to, read the code. We're going to walk through what we're doing here. So complete the trace object in VC. So obviously we need to go here. So if VM is null, then we're just going to return. That's fine, right? And then what are we going to do? Oh, let's do this part first. So if we're going to say, all right, if obj is null, then we're going to return, right? If obj is marked, then we're also going to return. Why are we going to return here? Well, we don't need to trace marking it anymore. This thing has already been marked. We don't need to do any more stuff. Okay, so that's like, we're going to trace through marks. If this thing's marked, we're already done. That's good. Okay, so trace blacken object. This is kind of phase 2, right? Where this is sort of this idea that we're going to go through and check from all the marked ones. We're going to sort of color in the ones that are directly reachable from roots, which are the only things that are still alive. You can think about how like a cycle that's just sitting alone. Okay, it's cool that it has references to itself, but it's not referenced from an alive part of the program. So we'll be able to garbage collect that out. So trace blacken object, let's follow our instructions here. So if obj is null, then we'll return, right? Otherwise, let's switch on obj kind, again, like you've been seeing us do quite a bit. And let's do case integer. What are we going to do? Nothing. They've got no references, so we can just return. Case float, no references, so we can just return. Case string, nothing. Interesting this time, right? Because string, though, even though it's dynamically allocated, is not a container type. It can't hold references that aren't to itself. So now we go case vector 3. What are we going to do now? We're going to go trace mark object on gray objects here. The same thing that we've got here. And obj data v vector3 dot x like this, right? And we'll do the same thing for y and for z. So trace mark the objects, make sure that we mark y and that we mark z. That's good. And now the last one is for case array. What are we going to do? We need to say call trace mark object on each element. So we can do exactly what we've been doing for each of these times before. Int I is, I is 0, I less than. We could say snake array t array, right? Is this a pointer to an array, or is this actually the array when we store it inside of here? Snake object h, we store just the array itself. Okay, great. Array. We'll do obj data.v array. So we go array.size I++. What are we going to do inside of here? We're going to call trace mark object on. And in this one, we could just probably easiest snake array get, and we can just say array and I. So that's probably the easiest way to mark those. We'll make sure that we're reusing our functions inside of here. And so now we need to go back up to our trace function here. So we need to create a new stack with a capacity of 8 called gray objects. So let's go ahead and do that. Stack t star s is stack new 8. If s is null, then we're going to return. And let's actually call this instead gray objects, just because it's a little easier if everything's called the same stuff here. All right, and now what are we going to do? Iterate over each of the objects in the VM. So, okay, for int I is 0, I less than VM objects, and then this is dot count, right? Actually count like this, because this is not an array, this is our stack, right? So we just need to remember which one is which. We have count and then I++. So what are we going to do with this inside of here? We're going to go and say, iterate over these. If the object is marked, push it onto the gray stack. So stack push, and in this case we need to do gray objects. And we'll do obj. We didn't actually check this, so we can say a snake object t star obj is VM objects elements I. Okay, so if obj and obj is marked, and we're going to go here like this, right? We're going to push this onto the stack of gray objects. Gray objects are the ones that we still need to process, but that are marked, right? And so now we'll iterate over all of the objects. We get the elements, or sorry, this is actually data. I did this last time. Data, and then we're going to push this object onto our gray objects. So now what we need to do is we need to do a while loop for while the stack is not empty. So we can do while gray objects count greater than 0. What are we going to do? We're going to pop an object. So we'll get snake object t obj is stack pop gray objects, right? So this will just get us an object off of the stack here. We'll get to iterate off of this. And then we can call trace blacken object on gray objects and obj here. And then once we're done, we just need to maybe do stack free gray objects here like this, and then we're all set. So if we wrote everything correctly here, what we should see inside of the test is basically we'll do something like create some integers, create a new vector, put those integers inside. None of them are marked. When we reference the vector and we mark this, all of these should be marked because they are marked sort of by proxy of being held by the container that is marked. So we might have a few type errors or a few small things inside of here. That's totally fine. Passing argument to parameter array here, but we did not do that. Where did we do that? On VM40. The array, snake object array, get, I, trace mark object. Oh, right. This needs to have gray objects here like this because that's how we mark those. That's okay. Nice. And then we need to do snake array t to parameter of incompatible type this. We can actually just say obj. We don't even need to do that here. That makes sense. Let's see what else we've got for compilation errors. Probably a few. Oh, okay. Nice. All right. So we're closer here, but let's see. Ooh, we need to make sure that when we trace blacken an object here, let's go back to do this here, which is that we haven't inside of trace blacken object. If object is this, we don't need to do anything. If it's a vector3 called trace mark object on x, y, and z, yep. And then we need to break, of course. Oh, I bet that might have been the problem there. Let's check that out.
Classic. You get bit on that for sure as you're running this yourselves. Okay, so let's see. X is marked is not true. Let's go check our main here. So it should see that X is marked. New snake integer VM XY. When we create a new snake vector. So let's go to new snake vector in here. New snake vector. Well, that shouldn't need to change anything, so that's fine. When we mark something from, oh my goodness, trace mark object, we didn't do anything here. We need to do this, trace mark object. Let's go back to here. Let's make sure we did everything here. Or already marked, return immediately. Otherwise, mark the object. Obj is marked, is true, and stack push gray objects, obj. Right, we actually need to mark the objects at some point. This is an important aspect of this. I was like, it did seem like we forgot to do a step here. Yes. Okay, this is the really important part. This is the thing that actually says, hey, we've seen this object now, and then we also need to make sure that we're putting this onto our list of things that may yet still need to be checked. So now when we run this, I believe I've solved all of them. And we get that. Great. When we run through this, we should get the whole pass here. And so now we have a way to be able to mark all of the objects and trace their connections through containers to any other data type that we have. And that brings us to our final lesson of the course. Thanks for hanging along this far. I hope you've been enjoying it. And this part's actually pretty easy. Sweep is really nice. Trace was definitely the hardest part of this garbage collector. So now every object has is marked. So we just need to iterate over them and free any object that is not marked. Easy peasy. Once it's freed, we remove it from our VM. One more thing, as a note from me, as it's not obvious about sweep, is that any object that is marked, we need to make sure that now we reset it to is marked as false, so that next time we do a garbage collection pass, we're going to reset everything then. So this just saves us iterating over and clearing everything at the start. This will just make that quite simple. So how are we going to do this? We need to iterate over all of the VM's objects in sweep. So for int I is 0, I less than VM objects count I plus plus, boom. All right, so if the object is marked, we'll just go snake object t star obj is VM objects data I. Yep. We're going to go if obj is marked. What are we going to do? We're going to say obj is marked is false. Else, we're going to free the object and set the data at that position in the stack to null. So now we can go snake. Did we call it snake object free? Snake object free. Nice. Snake object free. And I don't think we even need to pass the VM or anything. Nope, we just pass the object itself, obj, like this. And then we can set the data at that position to null. So we can go VM objects data I equals null. Cool. So we've just cleared that out. That'll make sure that we have null there in the future. And once we're all the way done, we have a little function that we wrote for you because it's not that exciting, which just removes all of the nulls from a stack. You can go ahead and look at that if you want in here, which just looks like this, which basically says, hey, let's go through here. We're going to pull down the items that are not compacted, and then we'll update the count, and then, maybe we'll zero out everything at the end just to be safe. So that's all we're doing there. We're going to null those out, and we're going to remove those nulls. Very cool. So that's everything that happens there. That's the sweep part, right? Which makes sense. If it's marked, we'll mark it as false. Otherwise, it wasn't, so it's free. Nothing's touching it, and we clear that data out. And now the only thing that we need to do is we just say mark VM, trace VM, sweep VM, like this. And I don't think any of those functions have anything else, but let's go ahead and hit submit and see if we got everything right here. Congrats, you have now hung out and finished the course. Hopefully what you've gotten out of this is a much better understanding of what's going on with memory management. Hopefully it's demystified both a lot of what happens in holy cow, Stas, make me look like a fool there. Oops, I did it already. Hopefully this clears up some of what's going on with manually managing your memory, so that you can sort of see that what's going on in C is not magic or mystical. It is just keeping track of some lifetimes and then calling the appropriate code when you want to free or allocate something. And now you can understand that your garbage collector does that for you automatically by running algorithms in the background, basically, right? And so
The thing to think about is, regardless of sort of what you're doing in, your backend or software developer journey in general, creating a bunch of objects for no reason can cause your garbage collector and your operating system to spin up, allocating all this memory, doing all of this work, only to just free them later for no reason. This happens a lot in like JavaScript if you're doing different kinds of like filter map or trying to write JavaScript like it's OCaml, but it's not. These kinds of problems can greatly decrease the performance of your otherwise could be fast application. And so using this knowledge, you may be able to see and pick up some of that hidden cost. That's my goal, at least, of when you're writing code, that at least now you're thinking and acknowledging what's going on with this memory management stuff. I hope you enjoyed this course. If you liked it a lot, of course, and you want to try out other stuff on Boot Dev, you can use promo code TEEJ, that's TEEJ, for 25% off if you made it this far in the video. And thanks everybody. Thanks Lane for having me on this course. I had a lot of fun and I finally recorded this. You can cut that part out, Lane, if you want, but I don't care. I'm happy. Bye.